Great. Yeah, thanks, Will. So we have like 5 minutes, a few minutes until we start. And so we'll start off again with a series of long talks, and then we'll transition into some lightning talks. We'll have a coffee break in there. Happy Groundhog Day. This is a picture of my backyard, not from this year, but recent. It looks the same. We got a lot of snow, which is really fun. But you know, we're all on
NCAR's even closed today, which is even more exciting. It's a good thing for having the meeting virtual.
That's right. NCAR facilities closed before they closed the county schools. So I was impressed by that. Yeah.
Yeah. Interesting.
But I guess
excited.
Yeah.
Oh, go ahead.
I was going to say, I guess NCAR knows the weather. So
Got the down though. I still really like watching the news and just seeing at the bottom of the screen all the school districts that are closed. And so it's like the whole state of Colorado is closed today, including like the state government. And my kid's school district is on virtual school. Like they're in class right now. Just like totally takes the magic out of a snow day.
Yeah, that seems unfair.
It totally does. It's like, well, we have the superintendent has like, well, we have the technology to do remote learning, so we might as well do it.
Yeah, so I told my 9-year-old if he needs to interrupt me, he has to come and help moderate the session briefly.
I hope we get to see him.
We'll see. He's excited about a day of Minecraft and Pokemon TCG. So I don't know how useful he would be at answering questions about the river routing. And so Inna is our first speaker. Inna, you are here. I saw you already. Great. Does anyone else have any announcements that they'd like to share or thoughts about the earlier portions of the meeting? If you guys feel comfortable, turn on your video so we can appreciate our little community for 2 minutes at least. Yeah. Oh, thank you. Excited.
Good to see everybody.
I just wanted to add a big thank you to Will and Dave. My last slide that I didn't get to was thanks very much for the use of the allocation.
Yeah, glad I went to good use. It's cool to see that stuff.
Yeah, certainly community development. So that's useful for everybody. Yeah, so Will, how many nations do we have joining us? We have people from all over the world.
I don't know. Maybe we can do a poll coming or something. Or people can put in the chat if you're where you're calling in from.
Oh, that's a great idea.
Outside the US.
Yeah.
Yeah. It's if you're outside the US, you can put in the chat where you're coming from. I'm sure it's all different time zones.
We'll consider Canadians to be outside the US.
Yes. I know that they would consider that.
Why on earth wouldn't you?
That was directed at you.
All right. Well, people are putting in their locations, their countries of, I guess, where you're seated. Inna, why don't you go ahead and share your screen and we'll get started. We'll be hearing about evaluating the reservoir parameterization in a vector-based global routing model suitable for Earth system coupling.
Yes.
Inna, we can see your slides and I can hear you. So go ahead and get started.
So, good morning or good afternoon from Brussels here, no snow. So yeah, I'm Inna van der Kelen, PhD student at the University of Brussels, supervised by Wim. And in the last phase of my PhD, I investigated how we can account for human water management through dams and reservoirs in CTSM. And so this work has been done in collaboration with Sherwin Gararia, Naoki, Mizukami, Martin, Dave, Sean, and others. So here you see the major water pools of the global hydrological cycle in the Anthropocene. So human activities play a very important role through groundwater pumping, irrigation, water diversion, and the construction of dams and large reservoirs. And so these reservoirs control more than half of the variability in global surface water storage, and thereby have a large influence on the seasonality in global stream flow and water availability. But despite its importance, human water management, and in particular reservoirs, are generally not included in Earth system models. And so therefore, our goal is to represent reservoirs in Earth system models. And in these contexts, there are two major elements. So the first one is to represent reservoir construction and the creation of open water surfaces due to dam construction. And so in the 20th century, reservoir construction increased, and now about 9% of global lake area are reservoirs, which is about 2.3% of global land area. And so we implemented this reservoir expansion in CTSM by accounting for dynamically changing lake tile. And we updated the CTSM lake surface maps based on the hydro lakes and global dam and reservoir data set, accounting for this increase in lake area. And so the second big element is the regulating effect of reservoirs on river flow. And here you see an example of the Bhumiboy Dam, which is an irrigation dam in Thailand, where reservoir inflow is stored during the high flow seasons and is then released again to irrigate downstream during low flow seasons. And so to account for this in an Earth system modeling framework, we need to go to the river routing model. And so that's the focus today, how we can account for these operations in MISEROUT, the new model to be coupled to CTSM. And in this respect, we don't need to reinvent the wheel, as there are already specialized hydrological models which account for this reservoir and dam operation. But due to the nature and global scale of these ECSMs, the lack of global information on dam operation, we need generic rules to mimic human decisions. And a range of global parameterizations exists from global hydrological models, of which we choose the Hanasaki method, mainly because it's low data requirements and it is a widely used parameterization and developed upon in many global hydrological models. And so in the remainder of the talk, I will talk about how we implemented and evaluated the Hanasaki parameterization in the river routing model MISEROUT for eventual coupling to CTSM. But first, we need some ingredients. The routing model MISEROUT is a vector-based model which uses the gridded runoff from CTSM and remaps it to each HRUs or catchments, and then routes the river, the water downstream along the vector-based river network. And so here we used a global vector-based river network topology on which lakes and reservoirs from the hydro lakes and grant databases are added as segments on the network. And the second ingredient we need is the reservoir parameterization of Hanasaki, which is constructed to minimize intra and interannual variability while accounting for water demands on outflow. And so for every reservoir, the monthly target release is set at the mean annual inflow, and here there is accounted for the fact whether it's an irrigation reservoir or not. As for irrigation reservoirs, the seasonality in irrigation water demand downstream are taken into account. Then the actual release is determined based on how full the reservoir is. And here a distinction is made between small reservoirs or within the rear reservoirs, where the actual release is actually influenced by inflow seasonality, as these reservoirs don't have the storage capacity to store multiple years of inflow. And so the main data requirements are the reservoir purpose, inflow, and irrigation demand seasonality. So because we need this irrigation demand for individual reservoirs, we developed an irrigation topology, dictating actually which HRUs or catchments are requesting water to each individual reservoir based on simple rules. If one of HRU is provided by more than one reservoir, we scale the demand by the reservoir capacity. And then finally, by intersecting the CTSM irrigation water demand with the vector-based HRUs, and then applying the irrigation topology, we can calculate for every reservoir the irrigation water demands and that the parameterization needs. So we use this implementation in different meso-route simulations to evaluate its performance. And so first we performed local simulations with meso-route using observed reservoir inflows from 26 individual reservoirs. And here we used the irrigation water demands, which we derived with the irrigation topology and its CTSM global irrigation water demand simulations. Then we performed global simulations using the HDMA river network with lakes. We present many reservoirs, and we use the gridded runoff from CTSM, which we remap to the meso-route river network. And so we performed 4 simulations, one without lakes using runoff river as outflow, one with natural lake parameterization, one with the dam parameterization of Hanasaki, and then a 4th one with the dam parameterization, assuming that all reservoirs are non-irrigation reservoirs. And then comparing this with the dam parameterization allows to assess the added value of accounting for these irrigation water demands seasonalities. So here you see the results for the meso-route local simulations shown by the clean efficiency, outflow and storage. And this shows basically that accounting for reservoirs give better results than for natural lakes, and much better results actually than compared for not accounting for lakes. And this is clearest for storage, especially for increasing capacity, reservoirs with a high capacity. They show really an increased value of accounting for reservoirs by regulating the outflow. Now, what I didn't show here is the comparison between the irrigation and no irrigation simulations, so accounting for irrigation demand. This is because they don't show a large difference. So here you see an example of a seasonal flow with the orange and the yellow curves, the orange being the one with irrigation demands and the yellow without irrigation demands. You see the difference is very small, and this likely points at underestimated irrigation water demands from CTSM or from the irrigation topology. So when we look at the results of the global simulations, the good news show is a bit over. Overall skill is reduced with more negative KGE values, but we still see an improvement compared to no lakes. But overall, we find similar skill of natural lakes and reservoirs implementation. And this is the same for reservoir storage, where the added value is even less apparent. But still the skills are better. The skill is better for these large capacity reservoirs. Yeah, and the main question is, what's the reason for this discrepancy also between the local and the global simulations? And the answer to that are biases in the simulated inflow. If you don't get correct seasonality in inflow, you won't get correct seasonality of outflow, and the added value of accounting for reservoirs there is left because the inflow seasonality is a major parameter. Then look at these biases in inflow seasonality. We zoom in the reservoirs in our data set located in the United States and Canada. And yeah, we see clear biases both in timing and magnitude. You have the blue curves depicting the simulated inflows, and the black ones, the observed inflows. And as these river inflows come directly from the routed runoff as simulated by CTSM, the first potential suspect is actually this runoff. And so here we show the biases by comparing simulated runoff with the global runoff reconstruction product GRUN. And we see like large biases in mean runoff. And we can actually categorize them, reservoir biases, in different groups. So first we have the large multi-year capacity reservoirs like Garrison and OHG on the Missouri River, where we see large overestimations of inflow. And so potential reasons for this are unresolved dams on the river stream network, more upstream, or overestimate runoff in the catchment. And this could be due to the fact that water abstraction is not included in CTSM yet, or that there is an underestimation of the irrigation water use upstream, and therefore too much water is put into runoff. A second group of reservoirs have their headwaters in mountainous catchments, and they show biases in inflow timing mainly, of which the annual peak arrives too early in the year. And potential explanations for this could be biases in modeling snow and melt dynamics processes in CTSM. And we did several sensitivity studies here, and we tested the sensitivity, for example, to meteorological forcing by using a 0.125 degree CTSM simulations with NLDAS forcing, but this did not improve these biases. But still, despite these biases in inflow, the local simulations showed that accounting for reservoirs clearly has an added value in simulating stream flow if these biases would be accommodated. Therefore, we evaluated the added value for global stream flow, looking at global stream flow indices here, looking at mean flow. We only use the stations on the river network that are maximum 200 kilometers downstream of a simulated reservoir. And here you can see on the purple colors, comparing the dam simulation with the no lake simulation, that accounting for reservoirs actually increase the skill in simulating mean river flows. So these results provide a lot of food for discussion, but I will go quickly over it as I have 1 more minute left. So we saw a little effect of the irrigation water demands, which could point to biases in irrigation water demands from CTSM or irrigation topology, although this appears to be less sensitive. The unresolved reservoirs upstream could be resolved by using a more detailed river network topology like the Merit Hydro. And the biases in the CTSM runoff could argue for an improvement of model processes or using a parameter calibration for runoff, of which Yifang will talk more about today, I suppose. And I will skip on this and just go to the conclusions. So we implemented a reservoir parameterization in Miseraut. This allows to model new variables, reservoir storage, which can be related to area and level through bathymetric relationships. We showed improved model comparison compared to the simulation without lakes, and we uncovered large biases in CTSM runoff. And this is all, now reservoirs are represented in Miseraut. So if Miseraut will be coupled...
you're at, I think you're a little bit past 12 minutes. So
okay, sorry. Yeah.
No, you're good.
I thank you. This is available in. This research is available as a preprint in GMD discussion, so I welcome you to go there for more details, and thank you.
Thank you. That was great. We have a comment from Maru Sulis. Would you like to ask your question?
Yes. Thank you very much. Great work and presentation. Is there any plan to link the activity to energy production? Hydropower, for instance?
Yeah, within my current research plans, there are no concrete plans to go for this, but our development would make this possible. Although I think there's still work needed before we can really go in these studies on improving the inflows.
Thank you.
Thanks. Keith?
That was a really interesting presentation, Anna. Thank you. I'm wondering about the feasibility of feedbacks going the other way. If there's restrictions about maintaining like a minimum stream flow coming out of a dam, if that could end up having upstream consequences on allowable irrigation. And when I start thinking about software implementations in CTSM, that starts to get mind-boggling with non-local connections between things. Have you considered anything like that?
Not at the moment, but I think these things would become really interesting to look at with this linkage with irrigation water demand and then reservoir operations to see whether our reservoir water is actually providing enough water for irrigation to sustain water for irrigation, and what the impacts are upstream and downstream. So I think these are interesting research directions for sure. Yeah.
Okay, we have time for one more question. Will and Dave are at the top of the list.
Go ahead, Will.
Arm wrestle for it. Well, Dave, anyway, I'm worried about snow and like how we're handling snow in the model, and it makes me concerned that even in these high res NLDAS simulations were still, you said that the inflow didn't really improve, which makes me think that we either have a high bias in snow or it's still melting too soon, or both of those things. At least that's what I've seen in a couple of model simulations, is if there's
Sorry,
too
hey,
much.
Anna, while you're answering that question, can you stop sharing? And then Yi, can you go ahead and start sharing?
Yeah, and so I guess the question is like, what do we need to do with snow? Or is there, it seems like there's indications that we're not getting snow right. I'm curious, that's obviously not your research, but if you have ideas or if you've seen things related to runoff that can maybe help us with how we're thinking about snow.
Yeah, I think that's really an open question to the whole community. To the whole community, I really don't have clear answers. But what is true is that, like, bias, if we're looking at inflow or runoff, like, these biases are just amplified because you integrate over a large area, of course. Like, but still, these biases are important to account for. We also tried sensitivity studies with the new hill slope model of Sean and different other sensitivity studies, but they didn't really resolve the issues. So I think more work is needed there. Yeah.
Okay, thank you. And our next talk will be from Yi Yao, development and evaluation of an irrigation scheme in CLM. Yi, we can see your screen. I can't tell if you're unmuted. Yes, you are. Go ahead.
I think I'm unmuted. Okay, thank you. Hello, everyone. Good morning or good afternoon. I'm Yi Yao, and I'm the colleague of Inna. I'm also a PhD student in Free University of Brussels, also supervised by Wim Thierry. Today, I'm going to present my research study. It will be the implementation and evaluation of aggregation techniques in the community net model. I will wait. So the presentation will be divided into 4 parts. Introduction, implementation, evaluation, and the conclusion. So firstly, I will have a very brief introduction. So actually, irrigation is the biggest wood use of human land management. But in different regions for different crop types, it is applied in various ways. As you can see here, we may have drip irrigation, we have sprinkler, we have flood, and also for the right parties, we have the pool techniques. And some researchers have already developed irrigation technique distribution maps. As we can see here, he divided the global irrigation technique into drip, sprinkle, and surface. But however, in current irrigation scheme in CM5, irrigation is applied individually. I would say irrigation is applied in the same way. So there's no different irrigation techniques. And here in the data set, there is only one variable which is called aggregated. This variable will determine whether this column of safety will be aggregated or just a rain fade. So we believe that it is necessary to implement different irrigation techniques in the model, and it may improve the performance of the model. So let's go to see how we implemented it. So firstly, we need to add a new variable in the surface dataset, which is called the aggregation method. So this variable can equal to 3 values, 1, 2, 3, which means the drip, sprinkle, and flood irrigation respectively. And actually, in this data set, for each safety in each pixel, we have assigned a different aggregation method, which means that, for example, for safety cone in 1 pixel, although the data set provides the fraction of flood irrigation, drip irrigation, and sprinkler irrigation, but we just use 1 safety, which is based on the technique with the most proportion in this pixel. So this is for limiting the computation cost. And this is the 6 irrigation techniques we implemented. So we have drip, sprinkler, flood, drainage, pool, and saturation. Please note that the last 3, drainage, pool, and saturation, is only for right parties. So the drip irrigation is actually is the original irrigation module. So every time when the soil water is less than a threshold, then irrigation would be activated, and the amount of water would be the deficit between target soil water and the actual soil water. And the water would be applied under canopy. And for sprinkler, we just changed the way of applying water. So in sprinkler technique, the water would be applied over canopy, which means that it's just like a rainfall. So there may be interception loss. And for flood irrigation, so compared to the drip irrigation, we just increased the amount of water. So now the water is the deficit between saturated soil water and the actual soil water. Because normally in reality, when people do the flood irrigation, the field, normally the soil would be a bit oversaturated. And then for the last three techniques, we developed a new surface water module. So this surface water module could hold the water into the field. As we know that in the red parties, there are always some water. So, and for drainage, the difference between drainage and the flood is just we have this new surface water module. And for pool, so for pool irrigation, every time when the water in the field, the water depth in the surface water depth in the field is less than 1 centimeter, we will do the irrigation and add the water and make the water depth back to 10 centimeters. And for saturation, for the last one, the difference between the saturation irrigation and the drainage irrigation is the condition of activation. So once the soil water in the field is less than the saturated level, we will do the irrigation. Actually, technically we just keep the soil water in the field at a saturated level. And so then we designed some simulations, and also we did some evaluations. Firstly, we did five global simulations. The period is from 1981 to 2015, and the first 5 years was a spin-up period, and the resolution is about 1 degree. So these five simulations are with different combination of irrigation techniques. For control, this is the original irrigation module. So for all the CFTs, we just use drip irrigation, and then for other 4 simulations, there's no difference for drip safeties, sprinkler safeties, and the flood safeties. But the only difference is for rice. For irrigation method, we use the flood, and for irrigation drainage, we use the drainage. For irrigation pool, we use the pool, and also for irrigation statute, we use the saturation technique. And to evaluate the ability to reproduce the irrigation water withdrawal, we collected the observed data from different sources. For the USA, we have data from USGS. For China, we have data from a recent study from Zhou. And then for other countries, we collected data from Aquastat. And here is the simulated irrigation water withdrawal with the old irrigation scheme. And as we can see here, mostly in most of the countries, the irrigation water withdrawal is underestimated, except the central China. And here we have the bias of 4 simulations. So the red means that there is underestimation, and the blue means that there is overestimation. I won't go in detail here because I don't think I have enough time. I'll just show you the numerical criteria. So we calculated the bias and IMSE for each simulation, and this calculation is conducted individually in USA, China, and other countries. And finally, based on this criteria, we choose the last one, IRI-SATU. So this combination as our new irrigation scheme, because you can see that in USA, it almost removed the bias and also substantially decreased the bias in other countries. However, there are a great overestimation in China, but we think as in our simulations, we did consider the water availability limitation. So we think overestimation actually is more reasonable, and also the saturation technique makes more sense physically compared to area method and area range. That's why we choose this one. And then we did some single point simulations. We selected three single point simulations, three single point sites from Nebraska, Castellano, and Mass. So these three places, they have three different irrigation methods. For Nebraska, it uses the sprinkler, and for Castellano, it uses the flood. For Mass, it's the saturation. It's a rice party. For each site, we designed three simulations. The first one is no IRI, which means no irrigation is applied. Then we have control, which is the old irrigation scheme, and IRI is the new irrigation scheme. So here is the simulated evapotranspiration, ground evaporation, canopy evaporation, and transpiration of different simulations of these three sites. And also for the first column, we also have the observed value. So as we can see, the model could reproduce the seasonal pattern of ET in all the three sites. But for Nebraska, so the first one, the figure A, there is a slight overestimation, and for Castellano, number E, and the Mass, number I, there are substantial underestimation. And the interesting part is that we can see that with the new irrigation scheme, which means that we use the saturation technique in the right parties, the ET in non-peak seasons, like from April to June, and then after October, in this period, the ET is greatly increased, and it is much nearer to the observation. As for other two sites, actually we can see that the difference between Ich or control to and the no IRI is very small. And here we have the delta ET, delta ground evaporation, delta canopy evaporation, and the delta transpiration for these three sites. The green line means the difference between the IRI and the no IRI. And the green line means the IRI means the difference between IRI and the control, which means the difference between the new and the old irrigation scheme. So as we can see, for ET, the new irrigation scheme, they increased the ET in all the sites, but for the different compositions of the ET, we have various results. For Nebraska, we can see that compared to no IRI, the IRI increased ground evaporation, canopy evaporation, and transpiration. They are both increased. But for Castellano and Mass, the ground evaporation is increased, but the other two compositions is decreased. And then
you're at 12 minutes, so please wrap it up. Okay, sorry. So yeah, for other slides, we have different results, and finally we go to the conclusion. So we think that the new irrigation module can improve the ability to simulate irrigation, water withdrawal in USA and other countries, but also the overestimation exists in China. And all new irrigation methods increase ET, but the effects on the other compositions vary. And based on this, we can think that it is important to consider irrigation method when simulating irrigation-induced impacts. And we think that CM with our new irrigation scheme is a suitable tool. So thank you. Thank you. We have time for one quick question, or we can save it for discussion. Okay, let's go ahead and save questions for, oh, Dave's got a question. Go ahead, Dave.
I'm just relating back to Ina's presentation, and I didn't catch the numbers exactly, like how much in a percentage sense has irrigation increased with this new method, and also don't know from like how low her simulations are implying irrigation is. Do you know if it's coming into agreement, or it's still way off what you would need for the dam parameterization results to look good?
Sorry, can you repeat it?
I think it's a hard question, so let me ask you in the chat, and offline we can.
Okay.
Yeah.
Thank you.
That's a good idea, Dave. Yi, if you could stop sharing your screen, and
Yeah.
then our next talk is by Yifan Cheng. We'll be hearing about moving complex land surface models towards actionable science, a novel approach of CTSM across Alaska and the Yukon River Basin. Yifan, we can see your screen, and you are muted, so go ahead and unmute yourself, and then you can get started.
Sorry that I thought
there
I
you
was.
Go. You got
sorry,
it.
I thought I was on mute.
Okay,
Anyway,
go ahead. Oh, you're back muted again.
Oh,
There
sorry.
You got it.
I don't know what happened. Hi everyone. I'm Yifan. I'm currently a postdoc at National Center for Atmospheric Research, and today I will briefly introduce high-resolution hydrological application and multi-objective optimization of the community terrestrial system model in Alaska. And I want to shout out to my collaborators, Andy Newman, Sean Swanson, Dave Lawrence, Keith Musselman, Joe Hammond, Danielle Kennedy, and Katie. So this is part of a nice navigating the new Arctic project, where we collaborate with indigenous Alaskan people and trying to estimate the climate impacts on Alaskan and Yukon rivers, fish, and communities. Under climate change, the Arctic is rapidly changing, including increasing air temperature and precipitation, decreases in sea ice, and changes in seasonal snowpack. The climate change also greatly influenced inland freshwater systems, and indigenous Alaskans heavily rely on them for subsistence fishing and transportation. The rapidly changing Arctic hydrology is influenced by complicated land surface processes. For example, the increasing active layer depth in permafrost greatly influences the subsurface runoff process, and the higher air temperature also leads to early snow melting, the frozen soil warming, which also greatly changes the stream flow seasonality. In this study, we use the state-of-the-science land surface land model, CTSM, for high-resolution regional application, and we're moving CTSM towards a more actionable earth science paradigm through optimization for hydrology-related applications. So in general, the spatial resolution we used in this study is 4 kilometers. So our study domain has over 200,000 gray cells. So it is very expensive if we run the optimization for the entire study domain. So considering the computational cost, we chose 4 medium-sized representative basins for optimization, as you can see from the left plot, including Kuparuk, Salcha, Beaver, and Toktina. And we will verify the optimized parameters at out-of-sample locations, as I show in the last plot, including 15 major river basins in Alaska. And we conducted a multi-objective optimization. Oh, shoot. Yeah, sorry, Siri, just being silly. We conducted the multi-objective optimization for river flow and snow water equivalent. And we use 1 minus Klein-Gupta efficiency as a flow objective. And Klein-Gupta efficiency is a comprehensive metric evaluating correlation bias and coefficient of variation. And for snow, we designed a congregated metric which evaluates relative bias in peak SWE, the snow persistent duration, and the snow melting rate. So in this slide, which shows how we configured a baseline scenario and how the optimization workflows, I will take some time to explain this. So first, in the upper box shows how we configured a high-resolution CTSM applications. First, we downscaled the ERA5 meteorological forcing data and using like a 4-kilometer meteorological forcing, and we used a high-resolution soil texture data and organic matters from soil grade. And in addition, we took advantage of the hill slope hydrology, which already implemented in CTSM by Shang, to account for the subgrade variability. And the low diagram shows the workflow for optimization. The first 2 steps aims to select sensitive parameters to Arctic hydrology. And then in the 3rd step, we conducted a multi-objective optimization for flow and snow. And we used a machine learning optimization method called adaptive surrogate-based modeling optimization, which due to the time constraint, I will not talk in detail in this slide. And based upon a preliminary optimization experiment that we conducted for each basin, we find that the optimized parameter shows great discrepancies for the basins in the northern slope. Here is Kuparuk, as opposed to the 3 southern basins. So we think it's because the Kuparuk River is located in the Arctic Circle and farther north than the remaining 3. So in this study, we leveraged the eco-hydrology region classification by the Environmental Protection Agency for a very simple parameter regionalization. So the optimized parameters for the northern basins will be applied to the 2 Arctic eco-hydrology regions, the Arctic coastal plain and Arctic foothills, which is highlighted by the blue boundaries in the right plot. And the remaining areas we will use optimized parameters for the southern basins. And you can see to evaluate this parameter regionalization, we have 2 domains that actually cross both the northern and southern regions, is Colville and Woolwich. So, later we will show the model results of like using the spatially distributed parameters as opposed to the singly optimized parameters. And in general, so the optimization framework developed in this study can be transferable to other CTSM applications. And we do believe it will be helpful and will become part of the CTSM community toolkit. So, and here I would like to highlight the perturbed parameter ensemble experiment, which is the ongoing effort and is the global sensitivity analysis for CTSM. The PP experiment can be extensively used in selecting sensitive CTSM parameters, not only to runoff and SWE, but to tens and thousands of, or tens and hundreds of other variables. And Daniel, Katie, and Dave will give a more detailed explanation tomorrow. So here, let's look at some results. So in general, the flow simulations get great improvement after optimization. The simulated flow, 13 out of 15 out of sample river basins in Alaska and Yukon gets improved. You can see the median clean Gupta efficiency increases from 0.4 to 0.63 after optimization. And this might be like not statically efficiency might be more familiar with, people might be more familiar with, increases from 0.17 to 0.57 after optimization. And I especially want to highlight the station called Yukon River, a pilot station refers to as Yukon P. And this place has a confluence area of 824,000 square kilometers. Its clean Gupta efficiency of daily flow increases from negative 0.76 to 0.51. And this, so which shows that the optimization is highly efficient given the total confluence area of the 4 optimized river basin only occupies 3% of the confluence area at pilot station. So as we mentioned before, Covio and Woolwich are the two basins intersecting with both northern and southern regions. So in the left plot, the blue dots represent the baseline scenario, and the orange stars denote the result using spatially distributed parameters, and orange circle and triangles denoting the model results using optimized parameters for single southern or northern basins. And we can find the model performance using spatially distributed parameters. The orange star outperforms the model performance using any single optimized parameters, which also highlight the necessity of parameter regionalization. So we also conducted a Shapley decomposition analysis to disentangle the contribution of each parameter, each optimized parameters for the flow performance improvement. And we can see that Arctic hydrology is influenced by multiple processes. And we want to highlight that half of the 14 parameters are not directly related with hydrology and snow processes, but with vegetation and sensible latent heat fluxes. And we can see the perturbed of the 7 non-hydrological parameters contribute to a total of 38.5% of the flow improvement in the northern basin. And the 7 non-hydrological parameter perturbation contributes 19% of the flow improvement in the southern basin. So, and also the different parameter contributions across regions reflects that the spatial heterogeneity of parameter sensitivities to Arctic hydrology. So here's the last slides. The takeaway message is the Arctic, including Alaska, is one of the most challenging regions in hydrological modeling because its complicated land surface processes, as we showed before, that multiple processes important to the river flow simulations. And our optimization framework improved the hydrological simulations there, which shows its potential for the use-inspired applications across the rest of the world. That's it.
Perfect. Great. Perfect timing. Thanks, Yufan. That was really exciting. Rosie, you can ask the first question.
Cool. Great. Thank you so much for this. This is awesome to see. I really like this idea of actionable earth science. I guess I'm pretty interested in the nitty-gritty of like the machine learning that you used for the parameterization, but that's probably like too much to get into in this question time. So I'll ask my other question, which is, do you have any plans to look at how the calibrations that you chose affect the other variables like leaf area index and carbon fluxes and so on, to see if the hydrology parameterization takes you into like a different part of vegetation space, if you will?
That's a very interesting question. So in the framing of our existing like research questions, we're not like going to look into like the vegetation and carbon fluxes or nitrogen fluxes right now, but suggested by Dave, I think we're potentially looking at other like permafrost in this study region, not only like focus on the river and the snow.
Which is of course totally reasonable, I should add. Yeah, nice work.
Thanks.
Thanks. So Yufan, if you could stop sharing your screen.
Oh, yeah.
And then Stephen, if you want to share your screen, but there's a question in the chat where Andy was asking, there's one basin with a long name at which optimization shifted early snowmelt later to match observation flow timing. And perhaps that parameter update would be instructive for INA. And so have you been in touch with INA, or that's something to consider?
Yeah, we have talked with INA And we do believe that the model framework might be useful to improve the inflow simulations for her reservoir studies implementing CTSM. But I think there will be follow-up work, but probably not conducted by Ina, but will be followed up by other students, other graduate students in her group, to further improve this study.
Okay, that sounds great. Thank you.
Yeah.
Stephen, I can see your screen, but it's the wrong display. So we're seeing the presenter view, and so we've got your current slide and your next slide. So if you could swap screens.
Yep, I will try to fix that. Does this work?
Yes. Okay, so our next speaker is Stephen de Hertog, Biophysical Effects of an Idealized LCLM on Climate. Go ahead, Stephen.
Thank you. So hi, everyone. I'm Stephen, and I'm a researcher at the Free University of Brussels. And indeed, my research focuses on the effects of idealized land cover and land management changes. And I just want to highlight that I'm working in the framework of the Lama Klima project, which stands for Land Management for Climate Mitigation and Adaptation. And there's also another colleague of mine who will be presenting later today about this project. So for this project and for this study, we did some Earth system model simulations. So I'll first quickly highlight the setup we used here. So we used 3 different Earth system models next to CESM, also the MPI ESM and the European Consortium model. And we did 5 different simulations. The first one being a control simulation, where we used present-day climate and present-day land cover conditions. And for all the other simulations, we preserved the present-day climate conditions, but we changed the land cover or the land management change. So the first simulation was a fully afforested world, so we converted all the land cover which wasn't forest to forests. The second one being the opposite, a fully cropland world, so showing all the entire world as a cropland. Then the 2 last ones were ones depicting land management changes. So based on the fully cropland world, we turned the irrigation parameterization on. So we tried to see how this irrigation affects a global cropland world. And the last one was one where we applied an extensive wood harvesting scenario to the full forest world. Next to these simulations, we also implemented an approach so that we could separate the local and non-local signals from the total signal in the biogeophysical effects. Now, going a bit more in detail here, what are those local and non-local effects for those who don't know? The local effects are defined as the effects which occur really due to the change in surface properties as a consequence of the land cover and land management change. So these are the effects you will only see within the grid cell after the change has occurred. While the non-local effects are more caused by changes in atmospheric circulation or advection, and these are also visible in places where no land cover change or land management change occurred. Now, how do we separate these two from each other in an Earth system model simulation? This is by applying a checkerboard, and that's what Johannes Winkler did here for the MPI ESM for global deforestation. And I will quickly show how that looks when you implement it in some of the land cover maps we see here. So here I give the example of the cropland expansion experiments used here. So on the left, you can see the regular land cover map that's present-day CSM climate simulation would use. I'm showing the percentage of forest in a grid cell. And on the right, you see how we implemented this checkerboard approach in the crop simulation. So we didn't really deforest or planted crops in every grid cell, but we did it only in every other grid cell. And that means that we only have half of the grid cells which are really underwent a land cover change, and the other half, the land cover change was preserved. So the effects, the climate effects which we see over these are only non-local effects. And these we can then use to correct the other ones to derive the local effects. So going towards the results, first thing I would like to show is an evaluation of our results. So we evaluated the surface temperature results that we found against observational estimates. These are generally satellite observations and also one study about the FluxNet data. And here on the left, I'm showing a latitudinal average of these observations within a range, the gray shading. And the three lines depict the local effects for each of the three Earth system models used for the crop minus forest, so really representing a full deforestation effect. And so what we see is that, yeah, first of all, we see quite some variation in magnitudes. But if we look at the consistencies and if we look at sign changes, for example, we see it's generally quite consistent. We see a warming over the tropics and most of the subtropics, and a cooling when going towards the boreal latitudes. This is confirmed by both the observations and the Earth system models. We, of course, have some biases, such as EC Earth, which is not showing this cooling in boreal latitudes, and CSM, which is showing a stronger cooling in the mid-latitudes already. But overall, we see the models are doing something okay. They sort of get the observational patterns. So we are confident that we can use them to study the effects of land cover changes. Looking at the results of all of local and non-local effects. So here I have a plot showing the effects from cropland expansion. On the left, you see the local effects, in the middle, the non-local effects, and on the right, the total effects, so the sum of both, and showing this for the three different Earth systems. So what can we really see? We see that the local effects are actually quite consistent across the Earth system models. Again, the magnitude does vary quite somewhat. You have much less warming in the tropics in MPI-ESM than you have in the other two models. But overall, they show the same patterns, warming in the tropics, cooling in the boreal latitudes. Now, when we go towards the non-local effects, this is not so true anymore. We see that there's quite a high discrepancy across the models, with a strong cooling due to cropland expansion in CESM, while MPI-ESM is even showing a warming, and EC Earth being somewhere between, depending on which region you look at. So you see that these non-local effects have more uncertainty related into them. Now, if we look at the same results, but then for afforestation, for the local effects, we again see a similar picture. We see again that the models are quite consistent, and they are showing the opposite signal that we had before, a cooling in the tropics and a warming in the boreal latitudes, as we would expect. Now, here, if we look at the non-local effects, we see that actually here, the models are consistent across each other. They are all showing a clear non-local warming caused by a global afforestation, which is, of course, an important result. Okay, then moving towards land management change. So here I show the results for irrigation expansion. So again, the same maps for the same models. I should note here that in EC Earth, the irrigation implementation there doesn't allow for communication of water fluxes between the land model and the atmosphere model. So here in this Earth system model, irrigation does not really cause any atmospheric effects, which is also visible from the results we get here, as there's almost no change to irrigation in this model. Looking at the other two models, though, we see that irrigation is clearly causing a cooling across in all the effects. In CSM, this cooling is mainly a local effect, which with some non-local cooling in the regions where irrigation is applied. However, in MPI-ESM, we see actually that the non-local effects clearly dominate and are much stronger than the local effects from irrigation. So there is still quite some uncertainty as to what is causing this irrigation cooling, although the cooling itself is consistent across the models. Then lastly, going towards wood harvesting, here I only am showing the results for CESM, as in MPI-ESM, wood harvesting does not provide any biogeophysical feedbacks, and in ECR, these simulations were not provided. So I can only look at the results for CSM for understanding this effect, and sadly, we don't really have much effect. So the local effect is barely visible. There's not really a local effect to the wood harvesting, and the non-local effects are more atmospheric noise, and there are no clear patterns. So we can sort of say that wood harvesting does not cause any clear effects on the climate on the grid scale level. So then, trying to understand these effects a bit more, we did an energy balance decomposition of the local effects for the different land cover and land management changes. So here I'm showing the latitudinal profile of surface temperature, and this being explained by the different energy balance components, with latent heat flux in light green, sensible heat flux in dark green, albedo in orange, and shortwave and longwave in different shades of blue. For the three different Earth system models in the columns, and for the different experiments in the rows. So cropland expansion, afforestation, and irrigation. So what we generally see is that overall the turbulent heat fluxes dominate. They really explain most of the effects. We see this is true for most of the areas for cropland expansion and afforestation, although albedo here definitely in boreal latitudes also plays a strong role. And this is definitely true for irrigation. We clearly see that irrigation, almost the entire temperature change is explained by the turbulent heat fluxes. What I can highlight also is that although the turbulent heat fluxes are important across all three models for cropland expansion and afforestation, the sign of change of these turbulent heat fluxes differs for EC Earth compared to MPISM and CSM. EC Earth is actually showing sort of the opposite of the two other models and also of the observations. So which makes us sort of see that EC Earth is giving the right temperature response, but for the wrong reasons. The changes in turbulent heat fluxes are going the wrong way. Okay, that's a bit what I want to say here, I think. Then moving to some general conclusions. So the local signals from land cover changes are generally consistent across the ESMs, at least in terms of sign. We have a strong, robust, non-local warming for afforestation, but this is much more unclear for cropland expansion. Irrigation expansion clearly showing a cooling, but it's unclear whether the local or the non-local signals dominate. And in general, these results have important implications for the application of these land cover and land management changes for land-based mitigation and adaptation policies. And so there are still some next steps. There's a lot to unpack in these simulations. We can still analyze the biogeochemistry, which a colleague of mine is doing. Also the remote effects, there's still a lot to understand. And these simulations, as they are idealized, are perfect for training an emulator to use in real life scenarios. The presentation of my colleague later today will be about them. And so these results are now sort of finished and submitted, and I hope you find it interesting. And if you had any questions, feel free to go ahead.
That was great, Stephen. That was really interesting. There are a number of questions in the chat, but let's go ahead and take a question from Yue. You have a question?
Yeah, thanks, Jackie. Hey, Stephen, very nice talk. Actually, I have a question regarding to the scenario design in your experiments, because it seems like all of these scenarios are very idealized, right? So actually, in realistic case, the land use land cover change dynamics could be very complicated. So if we want to, try to refer some like a climate mitigation, policy advices from your results. So probably we need to, rely on the linearity, between the idealized, for example, forest fraction change and also the temperature change, right? So do you have any insight, because in reality, the atmosphere could be very chaotic. So can we, do just assume like there's a linear relationship, for example, like 20% deforestation or afforestation or 80% afforestation, and also we can get, a proportion or like a change in the temperature?
Yeah, so that's a very nice question, and I'm quite sure my colleague who will present later on will have much more to say about that. But yeah, so these results are very idealized for the simple reason that they're also intended to be. So we really want to understand how the models perform and how well do they model these results, sort of understand it. In terms of policy use, of course, these data, as they are so idealized, are perfect to be used in an emulator training, which then also can sort of try to assess how the changes in if the patterns are linear or not, and try to understand this better and then apply it to more realistic scenarios. And apart from that, I also want to add that in terms of usability for mitigation policies, local effects are, of course, just to take as they are, because they are really defined only by the change happening within that single grid zone. So if you're a policymaker and you're thinking of doing some changes in land cover in a certain area, these local effects can give a good idea of what the climate response would be. you of course would not expect the non-local effect, because that would mean a really huge land cover change. But the local effects can already inform quite a bit.
Thank you, Stephen. If you could stop sharing, we are supposed to move on to our next talk, but James, do you want to have a really quick question? I know that you put a question in the chat as well. And then,
yeah, firstly, oh, sorry, Jackie.
Go ahead. And then Vim, if you could share your screen while James is asking.
I'm muted.
Yeah.
UA, you asked about more realistic scenarios. I'm currently involved with some work that's trying to do that, essentially, by trying to do afforestation scenarios that are constrained by policy proposals and trying to look at the effects of those. Just Stephen, really cool presentation. I thought the way you use those checkerboard scenarios was great, and some really interesting results across ESMs. Just to say, yeah, that I'm doing a project that looks at some of the same things that you are going to be looking at next in terms of atmospheric feedbacks, atmospheric chemistry, and so on. So it would be cool to talk to you about this further. I'll drop my email in a message to you. But yeah, really great stuff. Thank you.
That sounds great. Thanks, James. And our next talk will be Wim Thierry. Sorry if I pronounced your last name wrong. The kids aren't all right. I'm very excited to hear what this is about. Take it away. I can see you. We can see your slide, but you are muted. And you are unmuted. Go ahead.
Hi. Well, good afternoon, everybody from Brussels. I hope you can hear me well and that you can also see the screen. Please let me know if not. So jumping right in, as we have little time. The title of this presentation is "The Kids Aren't All Right." And when I gave this talk earlier, some of my colleagues came up to me and they asked me whether my kids are doing fine. Well, I can assure you that all of my 3 kids are doing fine. But this presentation is not about my children, it's about children all over the world, including potentially yours. Let me nonetheless start by showing you a picture of my youngest son. This is Gaspar, and Gaspar was 0 years old in 2020. And on the other hand, here's a picture of my mother, and my mother was 60 years old in 2020. So again, this is not about me, but might I ask you now to think about for yourself, if you can think about someone that is really close to your heart, be it your children, grandchildren, parents, or anyone else, and try to think of their age in 2020. And then we can ask a question that looks like this. Will a newborn experience more extreme events than a 60-year-old? And if you think that the answer to this question is yes, you might raise your hand now. I guess we're among climate scientists, so many will agree that the answer to this question is yes, of course. But then comes the next question. And the next question is, sure, but how many more? And then this is something that we actually have to, well, admit as climate scientists that this is something that we hadn't really quantified yet. I would say until recently. Now, this is a really important question for at least 3 reasons. First reason is that this is a matter of a question of huge societal relevance. Since 2018, young people from around the world have been leading these protest demonstrations by organizing school strikes, worldwide protest marches, and recently even hunger strikes to demand for more ambitious climate action. Now, meanwhile, countries are failing to meet the targets which they have agreed upon in international agreements, such as the Paris Agreement. And currently, with current pledges, we are heading towards 2.4 degrees of global warming. Now, this lack of sufficient climate action has this potential of turning into a generational conflict, whereby young people today don't have the power to make decisions, but will face the consequences of today's policy choices. And on the other hand, people that are in the driver's seat today, that are in charge and can make policies turn and change, they might not face the consequences of their decisions. And this has led into this catchphrase that some of you might know called "Okay, Boomer." Now, a second reason why this is a really important question is a legal one. We have seen also in recent years a surge in climate litigation, whereby people from all around the world are suing their governments, are suing fossil fuel companies for their contribution to historical impacts, and suing countries for their lack of climate ambition. And actually, many of these cases, it's actually young people that are suing their governments, and they are claiming that their child rights are being violated. So this scientific question has also important legal implications, because if a 15-year-old, for instance, will face more climate extremes than a 60-year-old or than any other generation, this 15-year-old is also potentially more entitled to start a lawsuit. Now, the third reason why it's an interesting and important question is a scientific one, and that is because it really calls for a paradigm shift in the way we assess climate change impacts. Let me illustrate this idea in the following slide. Here, you see a figure of how we typically assess aspects of climate change. You see a XY diagram with time on the x-axis, and on the y-axis a climate relevant variable, such as in this case land area annually affected by an extreme heat wave, a 1 in 100-year heat wave under pre-industrial controls climate conditions. And you see that this variable is rising over the historical period, and as we go into the future, we have these different potential future scenarios. And I'm highlighting here 3 scenarios: a 1.5 degree compatible scenario, a 2 degree compatible scenario, and current pledges leading up to this 2.4 degrees of global warming by the end of this century. And so under this 1.5 degree scenario, the global land area annually exposed to extreme heat waves will increase from the present day 15% to about 20% by the end of this century. Under 2 degrees of global warming, this fraction increases to about 30%. And if we're going towards current pledges, we're looking at more than 40% of the land area annually exposed to a 1 in 100-year heat wave event, a pre-industrial control heat wave event. Now, this common way of performing climate research does not allow us to quantify what climate change means for a real person born in a real location and in a real year. Because today, we are, let's assume we are still in 2020. If you look at someone who's 60 years old in 2020, this person was born in 1960 and will on average live until somewhere halfway the 2030s. And on the other hand, a child born in 2020 will on average live until beyond the end of this century. And so in essence, this newborn will live to see the day when one of these potential future scenarios becomes a reality. So what we did in our study is to quantify the lifetime extreme event exposure of different generations, of different birth cohorts in different locations of the world. Now, if you do that, you get a graph, and you can get a graph that looks like this. Here we have bar charts looking at the lifetime heat wave exposure for 2 generations, the 60-year-olds in 2020 and the newborns in 2020. We see that a 60-year-old will experience about 4 extreme heat waves, and that this number is very much independent of the future scenario. On the other hand, a newborn will face 17 extreme heat waves under 1.5 degrees global warming, and this increases to around 30 extreme heat waves under current pledges. Now, these absolute numbers, they are contingent on the heat wave definition. So what we did is we compared generations to each other. We calculate what we call exposure multiplication factors relative to a reference generation. And if you take the 1960 birth cohort as a reference generation, well, the 60-year-old will, by definition, face an exposure multiplication factor of 1, right? But if we do this, and for the newborns, we can quantify how many more climate extreme heat waves this generation will face compared to their grandparents. Under 1.5 degrees of global warming, this is a 4-fold increase. Under 2 degrees, a 2-degree compatible scenario, it's 6 times more heat waves. And under current pledges, grandchildren will face 7 times more extreme heat waves compared to their grandparents. Now, you can do this now for every generation born between 1960 and 2020. And then you get a graph that looks like this. This time we have on the x-axis the age in 2020, and on the y-axis the exposure multiplication factor. Now you can see that these lines, they lie on top of it, for the three scenarios lie on top of each other for all generations aged 40 years or older. And you see that the curves start to diverge for younger generations, with the strongest difference for today's newborns. So how did we obtain these results? We obtained these results by combining 5 state-of-the-art existing data sources. And this is why also the first bullet is why I'm in this session, because this database includes community land model simulations, which I've been conducting. The project with the impact simulations is called ISIMIP, or Intersectoral Impact Model Intercomparison Project. And these are global scale impact simulations with hydrological models, crop models, DGVMs, also health models, lake models, you name it. So we have these different sectors, and they provide cross-sectoral consistent impact projections. So we use that database and combine it with global mean temperature trajectories, and then 3 demographic databases, one on life expectancy, one on gridded population totals, and then one on cohort size. So we go beyond now these 3 marker scenarios, and in this research we assessed lifetime extreme event exposure for every realistic warming scenario ranging between 1 and 3.5 degrees of global warming by the end of this century. And then you get a graph looking like this, whereby on the x-axis we have our age again, and now on the y-axis we have the global warming level relative to pre-industrial. And we can fill up this 2D space with our exposure multiplication factor. And again, we get a graph looking like this. What you can do now is you can look up the age of your beloved ones, and for a global warming level, get the color and look up on the color scale how many more heat waves this person will experience now relative to a generation, a hypothetical generation living in under pre-industrial control climate. Now, let me just take one example. If we look at newborns under 3.5 degrees of global warming, this generation will face 44 times more extreme heat waves compared to the reference person living in a world without climate change. Now, in this research, so far I only showed results for heat waves, but in this research we performed this analysis for a total of 6 extreme event categories, including wildfires, crop failures, droughts, river floods, heat waves, and tropical cyclones. Now, for heat waves, you've seen already the graph. Now we constructed the exact same graph for all these 5 other categories, and then the results, they look like this. Please note that the color scale is different. For heat waves, it goes up to 30, and for all the other extreme events, it goes up to 4. Now, what you see is that, in general, the younger you are and the higher the warming level, the stronger the lifetime increase in extreme events. And just to give one example, if we look at a 6-year-old under 3 degrees of global warming, this child will face twice as many wildfires, twice as many tropical cyclones, 3 times as many river floods, 4 times as many crop failures, 5 times as many droughts, and 36 times as many heat waves relative to the reference person living in a pre-industrial control climate. Yeah, I'll very quickly show these gray graphs. They are highlighting.
We're at 12 minutes.
Yeah, I'll wrap up. I have 2 more slides. Okay. Just very quickly going into the regional results. We also performed these results on a regional scale, and we find that young generations in low-income countries will face the strongest increase in lifetime extreme event exposure. And this is problematic for 3 reasons. These generations contributed least to the problem. They're most vulnerable to climate extremes and their impacts. And today, there are a very large number of young generations and young people being born in these countries. Finally, you might think that we are all doomed if you hear about these results, but I would like to highlight that this is really not the case. If you look at this on the country level, you can see that young generations will face, in every country of the world, substantially more heat waves compared to their grandparents under current pledges. This is highlighted here by these dark red colors in every country. However, if we succeed in limiting global warming to 1.5 degrees, we drastically reduce this intergenerational burden, and in the case of heat waves, this is by 40%. which means that even under 1.5 degrees warming, young generations will still face increased exposure, but this is way less than if we would go towards a scenario of 2.4 degrees of warming. So this highlights the clear local benefit of limiting global warming to 1.5 degrees above pre-industrial. Good, I end here. Thank you for your attention. The paper is available online, and also I very much recommend to have a look at our website if you want to know what climate change means for you and if you want to share those results on social media. Thank you very much.
Thank you, Wim. That was a really compelling presentation, and it really puts it in a social context for us, which I think is really important. We don't have time for a specific question, but we are transitioning to discussion. And so maybe we could start off with a question for Wim. How do you pronounce your first name? Am I saying it correctly?
Yeah, Wim is fine. Yeah,
okay.
It's like Will in English, but yeah, Wim. Yeah.
And so one of the questions that I had looking at your the final slide where you had, or one of the final slides where you had all of the disasters or extreme events, was that I was surprised that there weren't more fires. And can you comment on that? With all of these heat waves, with all of these droughts, I do a lot of fire research, and so I was curious that it was smaller than I expected.
Yeah, so I mean, for sure, the strongest increase is for heat waves. And then I would say then we have 3 other categories: crop failures, droughts, and river floods, showing also, let's say, robust increase, but larger, smaller absolute relative changes. So the values are less, but the patterns are consistent. And then we have tropical cyclones and wildfires. Now, tropical cyclones, this is the TC downscaling model from Kerry Emmanuel that was applied to CMIP5 data. And we know that TCs are not so much increasing in frequency, but they're increasing in intensity. And this is something that we are not considering because we are only considering changes in frequency. For wildfires, so this is results from DGVM. So think about Orchidee, Joules, CLM. So the burnt area data from these models. Now, what we just find is that the spread in these models is huge. So we find huge intermodal differences for this particular extreme event category, much higher than for the other extreme event categories. And so, this is basically the multimodal mean of these. I can look up the exact number of impact models, but let's say 5, 6 impact models forced by 4 bias corrected CMIP5 VGMs, and that's what we are getting. So, you also need exposure, right? So this is also exposure. So there might be increases in wildfires, but perhaps not in densely populated areas, in contrast to these other extreme events. So that might also be one of the elements that is at play here. Yeah, thanks.
Okay, thank you. Will.
That was a great talk, Wim. I was curious, I guess kind of building on Jackie's, like after running through this with EasyMIP2 and then getting ready to kind of use EasyMIP3 again, there's obviously a ton of uncertainty in all of these metrics, but which one do you feel like, or which ones are the models just most inept at looking at? It's not surprising that we kind of agree on temperature and then are all over the map with everything else, but I'm curious, do you feel like with EasyMIP3, or maybe another way of asking would be, in EasyMIP3, do you think any of these metrics will show less spread among models, or like where have the improvements been made, or where do they need to get made?
Yeah, thanks. Well, that's a really nice question. So maybe first of all, what is ISIMIP? So the ISIMIP is like the CMIP of the impact models, and so what the coordination ISIMIP coordination team at PIC in Potsdam near Berlin does, they bias adjust CMIP data and provide also gridded input data sets for land cover and GDP population, and so they provide the framework, so the protocol plus the input data to do global scale impact simulations for pre-industrial, historical, and future scenarios. Now, ISIMIP2 is basically the CMIP5 generation of impact simulations, and now we are transitioning and have started the ISIMIP3 simulation round. So this involves forcing the impact models with CMIP6 data and then the latest generation of land cover projections and so on. What will be better in ISIMIP3 than in ISIMIP2? I think to start, the impact models will have improved. For instance, these runs were conducted with CLM 4.5, and my plan is to run CLM 5 for ISIMIP. I hope to start this spring and do these simulations over the next months. I know that, I mean, what is nice about ISIMIP is that very open. So I know within the permafrost sector, for instance, there's also indeed other teams that are going to run CLM in different configurations. So this will allow to assess the effect of different model versions. So that is perfectly possible that several teams will run CLM. Also, another element which is important is that there will be more GCMs. So 10 GCMs, that's 5 core GCMs plus 5 extra GCMs. So this more than doubles the climate forcings that can be considered. And then another element, which I think is important in this context, is that there is a new sector, the fire sector. And so while in ISIMIP2, let's say burnt area is somehow a byproduct of the biomes sector and the vegetation sector, we will now have fire MIP kind of like entering the ISIMIP framework. And we will have a whole bunch of fire-relevant variables, more models doing wildfire, and more explicit focus on that. And so I think that's also a very exciting development. Yeah, so ISIMIP is really a cool network, and all the data is both input data, but also all the model data is open. So if you go to data.isimip.org or you go to ESGF, you can download all of these simulations and analyze them.
Thanks, Wim. Can you stop sharing your screen, and then we'll continue with our questions. Sanjeev?
Yes. Thank you for the talk. It was really exciting to see, and in fact, I wanted that his screen like.
Okay, sorry. Go ahead and put your screen back up, Wim.
Yeah.
Apologies.
Yeah. So, yeah, this is not a technical question. This is just a comment. I like the metric that you created it. In fact, these are the more powerful metric to sell climate change to the people outside the climate science community. Because if you are selling climate change in terms of degrees C, I do not know why should I care, like if today is 10 degrees C temperature versus tomorrow is like 11 degrees C temperature. So the metric that you have created, it those how they can be brought to the like a policy discussion. When the policy discussion occurs, it should not focus on 1 degree versus 1.5 degree, but it should focus on how it is affecting the population, how it is affecting the society.
Thank you, Sanjeev, and nice to meet you also. Well, really appreciate that. And indeed, I think the power of this research is not the improved process understanding, but it's a different way of communicating the state of the art of climate science. And even for me as a climate scientist working already for several years on the field, it was quite astonishing to see the numbers, because it gets really intuitive and indeed. I mean, the difference between 1.5 and 2 degrees is often difficult to communicate. But if you say, well, your grandchildren will face a 6-fold instead of a 4-fold increase in lifetime heat wave exposure, that is something that people understand. You don't have to have a PhD in climate dynamics to understand this. So that is I think, what we try to do in this study. Yeah, thanks.
Okay.
And I can also say that we've written, together with an NGO called Save the Children, we've written a report. It's called Born in the Climate Crisis, and where these technical results are merged with like interviews from children from different places in the world to highlight also their vulnerability. And so you feel that indeed these numbers can then be merged with other elements, also with climate litigation potentially and so on. Yeah, thanks.
Yeah, thank you for the question, Sanjeev. Dave?
This is really more of a comment. I just wanted to sort of connect the dots of all the presentations this morning. I guess everyone already has done that in their head, but the previous 4 presentations were talking about how we can improve the model in ways that will help us understand impacts, adding reservoirs, adding irrigation methods, calibrating the model so it's more like the real world, and then looking at the impacts of land use change. And so just wanted to highlight that this nice set of presentations, good job, Will, putting them all together. And the thing I want to say is that, when you submit, I think Will made a point, maybe submit using CGSM 5.1, because there's some biases that's been resolved and bugs for ISIMIP 3. But the other thing is, if this calibration effort, which we're going to hear about more tomorrow, is successful, I'd be really curious to know how much that has on the downstream things like impact. So if we make a better biophysical, biogeochemical model due to parameter calibration, what kind of impact does that have? Because we've essentially not done that. We're just relying on these default parameter sets in all these impacts assessments. So no question really, but.
Yeah, thanks for that comment, Dave. And I think it really does, sorry, going out to shovel snow. It's a little noisy here. Hold on. We have a lot of questions in the chat. Apologies, that was distracting for me. There were a lot of questions for Stephen. And I think, as Dave was saying, putting this all into context, looking at how these different models handle things and thinking about the way that we could handle different mitigation processes is important. And so, Stephen, did you want to address some of the questions that came up in the chat?
Sure, I can take a bit. I've been trying to address them in the chat anyhow, but perhaps some things that came back with several people highlighting it, that I should look at the surface properties and the changes that really occurred and what kind of trees and everything. So yeah, this differs across the different models. We implemented, we used the native PFTs of each different model. So there's different kind of trees and different kind of complexities there occurring across the models. And also, there are a lot of differences in how the models respond. And so I already showed with the energy balance decomposition that in BC Earth, you have a completely different turbulent heat flux response to the land cover change, but also albedo, although all of them have a similar albedo change, where if you deforest, you have a strong albedo change. But in CSM, this seemed to be much stronger than in the other models, causing also some biases in the land surface temperature. Yeah, I'm not really sure what to add more.
No, that's great. Yeah, I think there were, and Abby, did you want to make any comments? I mean, I saw, Stephen, that you were addressing some of these questions in the chat, and it was exactly like looking at the differences and how the models handle things. Dave had a very good point about wood harvest, which Stephen, I saw you address. The way that CLM addresses wood harvest is it's very unrealistic. And so a better way to look at that would be through wood harvest, and the regular big leaf CLM just kind of makes a smaller box, but it doesn't really impart a change in structure. So looking at that with fates would be great. We haven't considered we're still implementing some things with fates in terms of a global parameterization of wood harvest. And then Marisa, do you want to make your comment?
Sure, or we can talk later. I was just wondering if, instead of looking across, since the 3 different models are imposing vegetation change in kind of different ways, if instead of looking at how the climate is responding across the imposed sort of PFT change, if you looked at the effective change in the surface properties and then looked at how the climate was changing across those surface properties, if they looked more similar or if they would still look super different.
Yeah, it's a good point. I would definitely think it's something interesting to do. However, it's a completely new study because these models, these PFTs differ. The changes that they influence differ. So there's quite a lot of work to go into understanding these things in such a way. And as for our project, the goal is mainly to inform on mitigation potential. We sort of want to go towards the large scale. What does deforestation mean? What does afforestation mean? And of course, the model diversity or the different ways of how deforestation and afforestation is implemented in the models is there, but we don't go into the nitty-gritty details of what they do. But although physically it would help understanding the patterns a bit better. Yeah.
Okay, thank you. Will?
I might kick it over to Abby, let her ask a question.
Okay, go ahead, Abby.
Yeah, I just wanted to follow up on that and say, I don't feel like you can do that without addressing some of the why. Like, you can't really say what the expected outcome is if you don't understand where it's coming from, at least a little bit. I don't feel like you'd have to design totally new experiments to do that, but you could still at least understand the responsiveness to how much those different factors change, like albedo or evaporative resistance or roughness length. And so that's why the wood harvest doesn't do anything, because it doesn't change those things very much on the land surface. So it doesn't have a biophysical impact. I still feel like you can't really make a statement that's policy relevant if you don't have some understanding about where that's derived from, and therefore whether it's a problem, how it's represented or not.
Yeah, no, it's a good point. It's a good point. I don't mean that you need extra simulations to do that. I definitely didn't mean that. I just mean that it's a lot more work to completely understand it and to make it the comparison consistent across the three different models. That's basically what I meant. I agree that's I only present surface temperature here, but in the paper I look a lot more at different aspects such as albedo. I look in detail since we have also some observational data sets of albedo changes, so we can validate those. So I try to understand what's behind these differences and how they differ, just not in the complete sense of things. Yeah.
Okay, thank you. Stephen, you're doing a good job of handling all these comments. It's a complicated study, and so we all appreciate that. And it was we're interested to read the preprint, and so when it does come available, please do share it. I'd like to go back to a question that was early on in the chat, and it was actually from Dave to both Yi and Yina. Are the increases in the irrigation seen in Yi's work large enough to resolve the implied low bias in irrigation from Ina's work? Yi and Ina, do you want to show yourselves and comment?
Yeah, I answered in the chat that we didn't really explicitly tested this, but I would expect that some of the bias would be offset. But to really understand where these biases are coming from, we would need really more observational data sets, but also on irrigation, seasonality and seasonal cycle, because this is what is actually key in these reservoir parameterizations, where you get the seasonalities, and these observations are, to my knowledge, not really available. But there are some approaches taken from remote sensing, for example, where this could be verified. So yeah, it could be potentially be already a potential explanation, but still we would need to define the problem a bit better, I think.
Yi, do you want to add to that?
I totally agree with Yin. I think it can help, but I'm not sure to how much degree it could. So we may need to test it.
I guess the other thing we haven't considered yet is water losses during transport, irrigation water, whatever it may be, channels. And, that's not considered at all. So that's another 10% effect or something like that.
Okay, thank you. Will, sorry, I missed that you had your hand up.
I dropped the question in the chat, and it was actually a two-part question, and I only put the first one in the chat. But I only briefly looked at the EasyMap3 protocol, but it's all the models are forced with GFDL forcing. Is that accurate, Wim? And so I'd just be curious, like when you do these runs, to see like if we can compare those results to ILAM and how CESM2 looks, or how those results compare to CLM run offline. And then also I was curious, like it seems like the EasyMap community maybe isn't, maybe I don't know if this is naive, isn't necessarily connected with the large ensemble community. And so, you know, within NCAR, we have this CESM2 large ensemble, which doesn't let you look at different scenarios, but it does let you look at kind of variability. And it seems like for a lot of the metrics that you're thinking about, a single model translating the results from a single model large ensemble into some of those impacts would potentially be really insightful way to contextualize some of the results from the large ensemble. More just a comment.
I just want to say that we are at our like human break time. And so I do want to allow Wim to address that or ask a question. And so what we're going to do is just go grab a coffee, walk around for a few minutes, and then we'll come back and we actually have a virtual coffee break where you can come in and there will be Zoom rooms available and you can go ahead and choose a room to join. You'll be able to see the people in each room, and so you can jump between rooms. And so before we go, I want to, Joshua Rady made this map. And so given Wim's talk, it's interesting that the people that are here are all in, we don't have a lot of people from underrepresented countries. So which is a circular argument. We're missing a lot of important people in our meeting today. So just something I thought that was compelling. And so with that, we will see you back at 10:45 Mountain Time. Will, do you have like a time thing? You had something the other day. Could you put that up while we're gone?
Sure, I can put that back up.
Okay, thanks everybody. We'll see you in a few minutes.
Will, are you still there in person?
Yeah, I'm here.
So we talked at the CLM, like one of the last CLM meetings, about doing a hike. Like somebody made a joke, let's go for a virtual hike.
Yeah,
I'm gonna do that. So
oh,
I don't
nice.
know how to, but I don't know how to, like, if there's a way to mark a break room with that, or like as a title. Can you put a title on a break room? I'll just put it in the chat. I'll just say what break room I'm at. I'm just gonna like walk around the trail.
Joshua, I can label one of them as with your name, dash hike. So
okay, that's fine. Yeah, if you just want to look, it's just going to be short. Like, are we still going to the top of the hour, or are we going to stop or go later because we started late?
I think we'll probably try to stay on schedule as much as we can.
Okay, it'll be a quick hike then.
Yeah, unfortunately.
This is an experiment. Hopefully I can make it work on my phone. All right.
Sounds good. Elizabeth, since I don't have any idea
Hi.
when people are, do you mind just opening up the breakout rooms, or are they already?
They are. I was just about to put something in the chat that people can
Okay.
from their room as they come back in.
Yeah, that'd be perfect. It might be kind of trickling back and forth. Do you mind pulling us back in at 10 after from the breakout rooms?
Sure.
You get to magically clap your hands and bring us together.
Yeah, I'm gonna write that down. So we had a high of 84 people I saw
Great.
today so far.
It was a cool session of talks.
Hey, Will. I haven't joined a breakout room yet. I was going to do that, but I saw you there. Good work. You've been busy with the rainfall.
I woke up this morning and it was bugging me. So after I got done shoveling, I made some.
No, that's actually really good, and it makes me think that. I mean, again, the idea of data quality is something we're going to have to emphasize in the paper. You know, but it also makes me wonder if we need to start sort of ranking these or categorizing the neon sites as, you know, in terms of data quality.
Yeah.
And because I think there was like an idea, you know, we can actually do sort of some gap filling or even using reanalysis data for precipitation. But when you start doing that too much, you know, you sort of aren't simulating exactly what was actually going on at that site, because you're getting data from other locations or even models. And so I wonder if that's something we want to consider is, yeah, we want to do all the neon sites, but maybe we have some top tier and second tier sites or something like that.
Yep. Yeah, I think that's a good point. I don't really know how to assess the data quality other than ones that are obviously bad, or ones that we end up using Prism data for or something else for gap filling.
Yeah, I'm not sure what it's just a way of trying, you know, going back to bio, you know, Roland Roberts, and saying, you know, this is a value added that's coming out of this project. You know, this is why you guys should be really interested in it. So
yeah, I agree. Do you want to continue the conversation on a breakout?
You know, actually, yeah, I guess we can, if you want to. I'm not sure who's listening.
Let's just
yeah, we can go
to room 6.
Go to room 6.
No one's there, and anyone can join us if they want to tuck me on. Allison, other. Here it comes.
Hello, everybody. That was nice. I hope you were able to, cute dog making an appearance. I hope you were able to get up and stretch your legs, have a conversation. We had a great set of morning talks, nice discussion. And so now we'll transition to a set of 5-minute lightning talks. And so Polly's going to keep time. She'll let you know when 5 minutes are up, and then we will not have questions in between the talks. We'll have questions at the end with discussion. And so Hedron, if you could share your screen. Sorry, and so we'll be hearing about parameters matter, improving soil and air temperature representation in an Arctic regional model using improved vegetation and soil boundary. Hedron, take it away. You're still muted.
Okay.
Okay, you're good.
Thank you.
Go ahead.
Okay, thank you. So actually a lot of people have talked about parameters in models yesterday and also today, and I just wanted to clarify here. I should have put external parameters in there somewhere. So basically I'm going to talk about changing stuff that is in your surf data file. But I guess all of you get what I mean, but it's not something you put into a title, but all right. So right, just very briefly where we come from. We run a regional model over the Arctic, which is an atmosphere coupled to CLM. And our main interest is in land and atmosphere interactions. So we need a good representation of the land surface processes. And we have a special interest in permafrost, which is kind of based in the polar research focus of our institute. And so usually when we think about improving our models, we think about process understanding and implementation of processes and increasing the complexity in our models. And I'm sure you've all seen this very nice figure that made where we see all those different processes that have come into the models through the last decades. And basically that means we incorporate more and more equations that often contain different types of parameters. And people have started to focus on those more and more in the recent years. But I think they are still not taken as important as they maybe are. So I just want to give 2 very brief examples. The first one is like the poster boy example of things, which is basically a soil temperature modeling at a specific site. So this is at Samoylov Island in Siberia. And so it's a very straightforward equation that you use to model here the soil temperatures, and it contains soil heat conductivity as one of the parameters in there. And on the left picture, you can see ground temperature is on the y-axis and years are on the x-axis, and then you have this temperature curve. And you can see the measurements in black and the model in this bluish colors. And basically on the left-hand side in the model, there's been a standard soil characteristics to model this. And then people went and looked at the core from the borehole that was actually used to make those measurements, and they adjusted the soil characteristics in their model. And then the result is the picture on the right-hand side, which I think is very compelling in and on itself. So this is a very local scale comparison, of course. You can look at other parameters on a more global scale. This was done in a paper by Liu et al. Rather recently. What they've done is they've exchanged the vegetation data in a global CESM setup from the NCAR standard to the ESA CCI land cover. And what you see here is just really a difference in surface temperature in winter, a surface air temperature. And I don't want to go into any details here. I just want to show you that
those make quite some difference and are statistically significant even in a lot of areas throughout the globe, and especially like also areas in the Arctic where I'm interested in. So I think that's also a compelling argument to why parameters really are important. So the changes that we've applied are just those that I've just shown you. We've changed soil characteristics in our model, and we've changed the vegetation distribution similar to the new paper from the MODIS to the CCI land cover. And this is run in an SP mode, right? So there is no evolving vegetation, it's just fixed. And so like I said, we're interested in permafrost, for example. And of course, if you change soil characteristics, you expect the soil to respond. And you can see in the top two pictures, the bluish colors are where the model has permafrost, and then the black outline is where the CCI permafrost product has continuous permafrost. And you can see over Alaska and Canada that some of the permafrost that should not be there in our model actually really disappears. And then on the other hand, we lose over Eurasia. We use some permafrost that should be there. So it's kind of a trade-off. And if you look into the bottom line, there is mean annual ground temperature at 1 meter depth, which shows you that the changes that we see through this soil characteristic changes especially are quite pronounced. So the differences are more than 4K in some places.
You're at 5 minutes now.
I'm at 5 minutes now?
Yes.
Okay. So there's also an impact on air temperature, which you can see here. And basically the bottom line is that parameters do matter. And if we change them, we get different results in the same model setup. So we should care about them. And that's the take-home message. Thank you.
Thanks, Hedron. And so now we'll transition over to Danielle Tuma. Danielle is going to be talking about extreme precipitation events and whether or not they alleviate drought and fire weather conditions. Danielle, we can see your screen. You are still on mute.
There.
And okay, go ahead.
Yeah, thanks for having me. So this is switching gears a little bit, doing more analysis rather than modeling. But yeah, so this is work that I've recently started doing here at my in my postdoc at NCAR, and it's very preliminary. So yeah, interested to hear any feedback at the end. So the motivation behind this work is to understand how and when extreme precipitation events may bust droughts. The motivation behind this is many events, but one recent event that a really intense atmospheric river hit California back in October. And many of us were hoping that this would end fire season or bust the drought. But actually, even though California received a lot of rainfall, it was not a drought buster. And even after a long season of wet events, we're still not out of fire season. So we're still seeing some fires pop up in California. So the questions I'm asking in this research is how and when do these events bust droughts or end fire seasons? And specifically, what does this look like in the CESM2 large ensemble? And how will these impacts change in the future climates? So first, I define extreme precipitation events by using the 99th percentile of the historic distribution. And I actually created a method where we can track precipitation events in space and time. So here you can see a maps of such an event over 3 days. And at the same time, I calculate the change in the 10 centimeters soil moisture daily anomaly after this event has passed. So you can see for this specific event, there's some wetting over the footprint of the event that I've highlighted in this pink contour. So here I'm showing the relationship for and the average daily precipitation for a given event versus the change in soil moisture for that event for 40 members in the large ensemble. Over Northern California in the summer season. So this is one of the dry seasons there. And in gray, you'll see contours for the historic period. And in reds, you'll see contours for the late future period. So you can see that almost all extreme precipitation events lead to an increase in daily soil moisture. So this is kind of a sanity check that, yes, when we get rainfall, the top layer of the soil wets. So that's good. We do see that events with higher average precipitation lead to larger increases in soil moisture. And we also see that in the end of the 21st century, there's kind of a shift in both the average precipitation during an extreme event, which we've seen in previous studies already, and as well as increases in the changes in soil moisture. So you can see this, these contours kind of spreading to the top right. I also wanted to understand if initial soil moisture conditions modified the impacts of an extreme precipitation event. So here I'm showing on the y-axis again in the change in the soil moisture anomaly on after the event has passed, and then on the x-axis this time I'm showing the soil moisture on the day before the event. So for 38% of the areas, they're dry before an event. And for these areas, we see larger increases in soil moisture over their footprints. For the other 62% of areas that are wet, we see smaller increases in soil moisture after an event has passed. We also see a shift between the historic and future periods. So we see that initial soil moisture tends to be drier, but also changes in the soil moisture anomaly increases after extreme events have passed. We also see that the tails of both distributions for both initial soil moisture conditions and changes in soil moisture become longer on both ends. I also wanted to understand the impacts of these extreme precipitation events on more seasonal scales. So what I'm showing here is for Northern California again. I split up different seasons in the historic period for the 40 members in the ensemble. I split them into different seasonal soil condition states. So from very dry in the red to very wet in the dark teal. You can see that. Okay, I'm almost done. You can see that there's not much difference between the average precipitation per event and how dry a season is in Northern California. And I've done it for other regions too. We do see that there is a stronger relationship between how dry a season is and the number of extreme precipitation events during the season, however. So these are just some preliminary results, and I definitely have some next steps that I'm interested in pursuing that I'll leave up here. And yeah, thank you.
Thanks, Danielle. That was really interesting. Next up, we will have Arshdeep Singh talking about the weakening of land use change driven cooling in a warming climate. We can see your slides and it looks like you unmuted yourself. Go ahead.
Thank you, Jackie. So I was scheduled to speak about weakening of the land use change driven cooling in the warming climate, but some progress I made, and now I will be talking on that only, but much more about how the soil moisture modulates the land use change impact under the global warming. So this slide shows the land use change impact on the near surface air temperature in the historical and future climate. So the left panel is the historical and the right panels are the future climate. And if you see the top two panels, these are for the total temperature change. So what we did is we took the multi-models from the CMAP6 LUMIP data and for the historical and future climate. And for historical, we had 2 experiment runs, which were historical and historical no land use. And when we computed that total impact of land use change on temperature, we just subtracted the historical no land use from the historical runs. And similarly for the future, we had ESM SSP 585 run, but we didn't have any ESM SSP 5 no land use, but we had like ESM SSP 585 126 land use. So we used that to compute the total impact in the future climate. And what we see is that there is we see a in historical we see a cooling impact, and like we see a warming in future at the annual scale. But then we also did it like we calculated the local impact of the land use change by comparing the climate change in the neighboring land use change areas and no land use change regions. And we see clearly like a significant decrease like or the cooling impact in the historical, while the opposite trend or the like warming climate like the warming or weakening of the cooling impact in the future. So then we computed like the energy balance, like how the energy balance performs. And if you here also, like if you see the left panels, these are for historical climate, and the right panels are for future climate. These blue bars are for effect of land use change on temperature, while these yellow will be showing the effect of land use change on energy budget. And so if we see like, since the historical for North America and Indian region I'm showing here, so for North America, if we see like there was a decrease, but there was like uncertainty in the energy budget. And if we see for the historical climate in Indian region, we see that the temperature was driven by the decrease in the net short wave and a sensible heat flux. And if we see in the future, where we see that there is a weakening or like the warming impact is increasing, there we see that there is a decrease in latent heat flux and net long wave, while there is an increase in sensible heat flux here. And for Indian region, we see that there is a decrease in like more intense cooling in the future, and which is because of that shortwave radiation is decreasing, and also sensible heat is decreasing. So we were like, what are the drivers of land use impact in the future climate? So here, since we saw that there was a gradual weakening of land use change in the mid latitude region, while like in the Indian region there was a strengthening of the cooling. So what was impacts were like we calculated the albedo change in albedo over that period of time, and we see that there is a increase in or almost the same albedo, while there is increase in albedo in the tropics. And when we see like how the soil saturation changes over the time, it was decreasing in the North American region and the Eurasian region, but in India it was increasing. So this was the main thing, like why there is a cooling impact in the tropics and weakening of the cooling impact in the North American region. So then we were like how to quantify the effect of soil moisture and land use impact. To do that, we used the Clapeyron relationship, which connects like the evaporative cooling with the three factors: the soil moisture, the vapor pressure deficit, and the land use driven radiative force component. So if we see this is like the DT, like here we say that a change in temperature due to land use, and here C is the function of soil heat capacity, surface resistance, and time scale integration, and is a constant term, while this V is a vapor pressure deficit, and this gamma here in this whole equation is the slope of saturation vapor pressure curve, and S is the change in soil saturation, and their DS is the change in soil saturation, and this S is the saturation level. And this I told earlier, this is like the land use driven radiatively forced component here. So when we use this equation,
we're at 5 minutes now.
Okay, yeah, this is last slide. So what we did, we just did a sensitivity analysis, and we found that by this equation we captures almost all the points, like how the land use change driven temperature, land use change impact on the temperature are there, and we see that there is a more impact of change in soil moisture than the vapor pressure deficit. So thank you.
Thank you, Arshdeep. Okay, next up we have Shruti Nath, integrating land cover with CLM feedbacks into climate models using the emulator approach. And sorry, that's LCLM. But Shruti, are you here? This is, I think, the complementary talk to Wim's talk.
Stephen's talk, I think.
Oh, Stephen's talk. My mistake, yes. Okay, I do not see our presenter. Okay, well, we can wait and see if Shruti joins us. But in the meantime, we can go ahead and turn on our cameras if you're comfortable, and we can transition to discussion. I'll put a message into the chat. Yeah, and Stephen, if you know if Shruti is going to be joining us. Polly, could you read out one of the questions? I'm gonna put a message in the chat well, I'll try to send an email. But
Daniel, do you want to ask your question for Danielle that you had in the chat that she hadn't gotten to yet? The others have been answered in the chat so far.
Yeah, sure. Yeah, Danielle, I was just wondering if you've looked at the time scale of soil moisture anomalies post-event. Like, does it take a week for soil moisture to kind of regress back to climatological soil moisture, or longer? And does that vary by the size of the event, by the prior soil moisture, that sort of thing?
I have not looked at that yet, and I think that's a great suggestion. And I also think that maybe looking at deeper levels of soil moisture on these different timescales might also be interesting. I'm not sure if there are more levels saved on the daily timescale for CESM2 large ensemble. I'll have to look into that, but yeah, definitely excited to dig into this a little bit more and explore those relationships a little bit.
Are you looking more at monthly data, or you must be looking at daily data? Or
so for the first half of the talk where I showed those like contour plots, those were using daily. So I found some daily 10 centimeter soil moisture. And so you can kind of see kind of the instant impact of the event, and you could look at it at longer timescales as well, as you suggested. But for the seasonal ones where I was looking at the relationship between for like a wet season versus a dry season, and kind of the statistics of events during those seasons, I was using monthly for that. So, and I'm pretty sure that there are for deeper levels of the soil, there are monthly data. So that's something that we could definitely look at and planning to look at.
Cool.
Yeah, thanks.
You know, you might also, there might be daily total water, or yeah, I might want to look at that, because that'd be interesting to know whether how the surface versus the deep soils at the daily time scale are responding. Like, is it filling up the whole column or just saturating the surface and then running off or something?
Yeah, that would also be interesting to see kind of in times where we do have a really large event and we don't get much change in the soil moisture. Is it because a lot of the water is running off, or it's already saturated, or see what's going on there too. Thanks for the suggestions.
thanks, Danielle. Steve, there's a question for you in the chat. Marisa said the land use change in the historical climate looks pretty different. Actually, Marisa, do you want to read your question, or do you want me to read it out?
Yeah, Sanjeev might have already just answered it. So from the maps, it looked like the patterns were pretty different, but Sanjeev's saying they're maybe actually pretty much the same, so it may not be a driver. But I was wondering if how much of the difference you were seeing was coming from the difference in imposed patterns of land use, and how much was coming from the fact that the land use change was getting imposed under a different climate. like a different CO2 concentration, so different temperatures and precip.
I guess I'll answer it. So yeah, thank you for that question. Land use change, or at least the data set that we have looked into, it does not increase in the mid-latitude. So mid-latitude land use change remains same in the future climate. You can see the thing in the even in the albedo change. Albedo did not increase much in the mid-latitude, but albedo did increase in the tropics like India because land use change is increasing there. So that's a land use change part. And so in terms of the pattern, mid-latitude is not changing. So it is likely because of the changing climate condition, or at least that is our thought process right now. Does that answer your question?
Can I follow up? I'm confused about land use versus land use change. Right. So the land use, like say, Arshdeep showed some results from the Midwest US, which I don't think is actually changing in terms of land use. Since it changed over the historical period, but it hasn't changed into the future. So it's the same land use, but it hasn't changed. So you actually mean the land use is the same, or do you mean the land use change is the same?
Yeah, so that is that terminology can be confusing. Land use change has not increased in the mid-latitude, and yeah, I agree that direct method impact it's basically there is no difference between two of the experiment. But when we do the local impact, we compare it against the pre-industrial climate. So all the analysis that was presented in the slide 2 and onward, that was only using the local impact because we have little more confidence there than the slide 1 top row plot.
Thank you for that clarification. There were some questions for Hidron in the chat, and then I know that you ran a little bit short of time, and so in the chat you said you didn't get to show a result for soil temperature. Do you want to show that slide now?
Yes, I'd be happy to. I mean, actually, the story was finished where I ended when I first set this up, where I just wanted to say, okay, look, if you change parameters, your response changes. But then I looked into how they change, and that was the thing that I couldn't show anymore. So I can try and very briefly show you this table. I think it's rather easy to understand also. I just need to, okay, let's see if I can share my screen again. No, why does this not work? There it is. Okay. Okay, so this is a comparison of soil temperatures in my model run versus soil temperature stations throughout the Arctic. And so there is on the top rows, it's bias. On the bottom rows, it's root mean square error. So we account for differences in both directions. And the color coding just shows you how extreme the differences are. And on the y-axis, there is depth. So it starts with 20 centimeters and goes down to like 3 meters and 20 centimeters. And basically, the tables on the right-hand side are a lot nicer than those on the left-hand side. And especially this extreme summertime bias that I have in the reference. So with the like standard data sets, becomes a lot smaller when I change the soil characteristics and vegetation. And actually, you can see that there is even an effect in air temperature. So it's a lot smaller. But you can again see that in the summer months, the bias of 2 meter air temperature in comparison to observational in situ sites becomes smaller. which was not my main point, but it's still really cool. So thank you.
Sure. Yeah, thanks for showing that. And so we have about 10 minutes left for our open discussion. And I know that so we can open this up to just general discussion. We can have specific comments to folks from this morning, or just these lightning talks. I don't know if we have further announcements. We'll be going to lunch. After lunch, we have another set of lightning talks, and then a little bit of discussion. And the meeting today ends at 2, so we just have a little bit more for today. Daniel, I see your hand.
Yeah, so on the surface data set parameters, Dave had asked, what the differences were between the two data sets, and we're doing this parameter perturbation experiment, and we thought it was important to perturb some of the surface data set data. And it was interesting that you swapped in two data sets. I think that's maybe like more sound of a way to do it. But what we did is just kind of pushing something like sand percentage, like plus 10% or minus 10% uniformly. And so do you have any ideas about the differences between those two approaches and which you think might be, I don't know, more robust?
That's a hard question. So changing sand changes a lot of things, especially if you do that in a top layer. At least where I do that, I change soil moisture very significantly, and then that changes everything else. So, I mean, perturbation sounds nice because it allows you to actually assess where your impacts come from, right? So I actually changed stuff gradually too. So I changed only vegetation, and then I changed only mineral soil, and then I changed only organic soil, and then I changed everything together. And but I didn't show that here because I didn't have much time, and then the results are pretty much what you expect them to be. So changing vegetation has a bigger impact on atmosphere than on soil. Changing organic soil has a bigger impact than changing the mineral soil components. And the mineral soil components actually did a lot to variability, which I didn't get to show either. So my maximum annual ground temperatures, especially in the top layers, changed a lot when I changed sand content.
Yeah, and yeah, for sure. And we're seeing the same thing, very sensitive to the sand perturbations. And so we're somewhat trying to understand, this is an important part of, uncertainty in our model is uncertainty in these data sets, but it feels like we probably aren't sampling the uncertainty correctly when we just kind of uniformly increase something or uniformly decrease something, because there's probably some spatial characteristics to the errors, and maybe swapping in two data sets is a better, I don't know, proxy for sampling some of the uncertainty.
Yeah, maybe. So the original idea from the group that made this data set was actually not to provide a single value for each grid cell, but they provide a range, and their model actually samples from that range, and they run an ensemble approach, which I could never ever afford. But it sounds like the thing to do, right? And actually that reflects, I guess, the databases that they come from also, because you have this range that is really defined by the borehole data that you have. But I have really no idea how you would incorporate that into a global model. So, yeah.
Yeah, thanks for that. Dave, I see your hand.
Why don't we let Polly go ahead?
I was just wondering if anyone has looked at soil sensitivity with fates turned on. I have not done that yet.
We're trying. But then we're still trying to get fates to run over our domain in a like reliable way. But we're planning to do that. So we are trying.
So I would, since we're having this conversation about input data sets, I don't think we're going to talk about this any time during the meeting. I think it might be worth showing people really quickly what Peter has done, which is compiled all the surface data sets. So I'm going to share my screen and then also put this into the chat. So this is a table showing all the input data sets for CLM right now and their source data. So
Hey,
this is,
sorry, Dave, can you make it a little bit bigger? I don't, if it's a pain, then that's okay. We can open it on our own, but
yeah, I mean, honestly,
that's
you
better.
have to
That's
look at it
great.
on your own, because I'll just show you how big it is. So it's, so this is all the input data that CLM is currently using at its source resolution, which then gets modified with a tool called Make-Surf Data Map for use in CLM. So we are sometime in the next few weeks, we intend to have a conversation about this list of data to see whether or not there are new versions that are better, things that we could do better. A lot of these things we haven't looked at in years or maybe even decades. So I think I just sent the link. Hopefully people can look at it. If anyone has any comments, I mean, we want, it's like beyond our capability really to track every single observational source data set that's out there. So if people know something that we should be considering, we'd really like to hear about it. And if you'd like to participate in that discussion we're going to have in a few weeks at the CLM meeting, let us know. Peter or Will, do you anything you want to add to that? I just thought I'd take the opportunity to raise this point.
No, thanks for bringing it up. Yeah, and just to emphasize, if people do have data sets that we should be aware of, to either add them to this or send me or Dave or Peter email, and we can invite you to the conversation that we have in a few weeks.
I'd just like to add that I'm currently finishing off the CLM5 land data techno, which is going to be a comprehensive, description of all the methods and all the data sources and how they're compiled. So hopefully that'll be in the next, short couple of months. That'll be available to the community. It's been a process to get it together. It's been complex, and what I wanted to do was capture the history of how we developed all these data sets as well. So looking at the versions of the model coming through, and has the capabilities of CLM changed, how we've been able to get new data and to do that. And so having that in one place and having it as a living document I think is really important. So thanks, everyone.
Yeah, thank you, Peter. We're looking forward to that. I can only imagine the amount of work. Sanji, if I see your hand up, and thank you, Dave, for sharing that link. Yeah, we'll I'm sure we'll include it in the agenda for the CLM meeting.
Yeah, it was quite scary to see their list, like, when did you start? One component is updating the data. Second component there is how to quantify the uncertainty in those data points and how those uncertainty can be incorporated when we run the model, either the parameter perturbation. So if along with that mean value, if I'm a standard deviation or any kind of measure of the spread can be also put, then a system can be developed where you sample the data from that distribution instead of using like a 60% of the sand or 30% of the clay. So is there a plan to put the standard deviation in addition to the mean value for the grid cell?
There's no plan. I mean, just period. There's no plan. We're just, but that is a good point. And that's a good advice. So if we have an opportunity to do that, as you saw, there's like 50 to 100 data sets. I'm not sure how many. So, it would take a huge effort to go back and find standard deviations for everything. But I think going forward, as we replace data sets, we should definitely think about doing that. We'll also note, I think Yukon had to leave because of some sort of family situation, but he has developed some code to allow you to modify spatially variable parameters like are on the surface data set for, the PPE is not addressing that really very directly, as Daniel just mentioned. So, at some point we're going to try to bring that in and allow either to modify data sets that already exist that are spatially variable, or for parameters that are currently considered to be globally constant when they shouldn't be, adding new parameters to that spatially variable data set. So both those things are sort of in the pipe. Don't know when they'll come, but something that we're thinking about a little bit. Recognize them. This is going to be a, again, going this actionable Earth system science paradigm. There may be lots of situations where you just can't really justify a global constant parameter value for things.
Thank you.
Yeah, thanks for that question, Sanjeev. And yeah, Dave, I thought that the UFON's application on Alaska, it really does point to the value of these high intensity regional analysis. And so, Hadron, I look forward to seeing the runs with Fates with your group, and get in touch if we can, I don't know if you're already talking to someone about getting Fates up and running. So if you want to check in about that.
Thanks.
Sure. So we only have just a few more minutes before we leave, but if anyone has any final comments, I see that Adriana put in, we've already got our next data set for soils. So Peter, don't hit finish yet. But I want to thank all of our speakers from this morning and this afternoon, and everyone for sticking around for such a great discussion. I'm sorry that I didn't get to go on the virtual hike with Joshua Rady, but that sounded really nice. We'll take a break for lunch. After lunch, we've got lightning talks by Nathan Collier, Sam Rabin, Sanjeev will be giving a talk, Naoki, and Sean Swenson. So a lot of model feature talks, which will be really interesting. And then we can have more discussion. Charlie is also excited about Hadron's optimism and getting another Fates user out there. We had a good day of Fates talks yesterday, and it's really exciting to see how all of these things can come together, because they definitely complement each other. And all of us Fates folks are excited to take over the world. And so Peter is pointing out that the documentation is going to be a living document, and so we'll be able to update that as we move forward. And then Dave Lawrence is saying that yes, Fates as a regional model, and maybe we can use it in Lilac. You want to comment on that, Dave? I hear about Lilac all the time, and I can never keep all these things straight.
No, it's Lilac stands for lightweight interface for land atmosphere coupling, and so it's the coupling infrastructure to couple any atmosphere model to CTSM. So Hydron had to go through the very painful process of coupling CLM to her regional model. And then it would have to go through another painful process if she wanted to do it again. So the goal with that infrastructure is that you only have to do it once, and then you can easily get the new updates to CLM as we go forward, and not have to redo that. But it's a project you'd have to undertake. But we're happy to try to help with that.
Okay, thanks for that. Peter, you've got your hand up.
Just a quick question on Lilac. Is other land surface models going to be brought in besides CTSM to the Lilac framework, so we could see other land models being able to be coupled to WRF in the future?
No, I don't think that's in the plan.
Okay, cool.
It's the goal is to do the opposite. So there's fewer variants and more unification. So kind of goes against the goal. So within CTSM, right, as you know, Peter, but I'll just say here is that we have a whole wide range of configurations now. ranging from the numerical weather prediction very fast version up to the full complexity fates. So that is the strategy, is that we are trying to build in flexibility in the system to be able to, for different applications, including, options to choose different parameterizations where appropriate. So.
Yeah, that's a really good point. And maybe we can make a note to talk about that in our discussion this afternoon. We're talking about new features, and maybe we could just, talk about how the plan is to allow users a lot of choice in terms of what features. And so even if you choose, like within Fates, you have the option of multiple features, multiple ways that you can run it. So, and I'm sure we'll talk about that more just as we move forward. Well, we don't see any more hands raised. Maybe everyone's ready for lunch. I'm gonna probably shovel some snow. My son did come in, but he was afraid to come on camera. He's still in his pajamas. He did not want to say hello. He wanted a piece of candy. And I said, you've got to come say hello. And he said, no, I'm walking away. Thank you, everybody, for your attention today. And we come back to the meeting at 1 o'clock Mountain Time. So we've got just about an hour for lunch and a break. Let us know if you have any questions, but yeah, see you in a little bit.
Hey, Will, do you have a sec? Oh, maybe not.
Yep, I'm here.
I was just gonna slight planning for the afternoon session.
Yeah.
I'll come back a few minutes before it starts by Jackie. Thanks. What do you have? I'd prefer not to keep time if you want to do that.
Sure. No, that's fine.
You feel okay with that? And then I can moderate questions and that part of it.
Yeah. So you'll introduce folks and.
Sure. Yeah.
Okay.
I just like when I do the timing, I can't pay attention to anything that's going on. I get so stressed out about missing the timing. So
it's hard too with I think it's all lightning talks in the afternoon.
Yeah. So if you
I don't mind doing that, and I'll interrupt people then.
Okay, great.
I'll be the bad cop. You can be the good.
So I'll do the introductions, and then I can help moderate the chat and bring up questions in the discussion.
Okay, that sounds great.
All right, thanks. Well,
right,
thanks for so much work you've done to put this all together.
Oh,
I will say you can ask for more help. Dave always used to ask us to help him a little bit with the schedule, at least. So
oh, good.
Yeah, he would make like a draft, and then he would send it around, and we would, maybe with questions that needed help still shuffling things. So anyway, you can ask for more help.
It was so late. It was so late because we split up, because I'd asked people if they wanted a short or long format talk, and by the time I got those responses, it was like, we just got to get this out.
Yeah, that's fine too. I don't feel like I need to sign off on it. I just want to tell you that if you need some more people to do some labor, like you can ask for some help.
It's all right. So I get paid the big bucks.
Yeah, exactly. Me too.
Yeah, exactly. You really do. All right. See ya.
Bye.
Well, I heard you talking, so I jumped back on here. Since the talk is the PPE thing is only tomorrow at the end, I just want to ask, like, I don't think I ever, I'm not at all the CLM meetings and stuff. So the sparse grid is what I think it is, right? It's like, it's distributed points from a larger grid.
Yep. Yeah. So Forrest went through, and he did this. He's done this a few times for different projects now, but he went through and picked and identified like the 150 points that would be most representative of the globe, or the 200 points or the 400 points that are most representative of the globe. And then that's what we're running the PPE in. Is not globally. We're not running a global PPE, for at least for the one at a time. We weren't running a global. We weren't running the model globally. We were just running it at these 400 representative points.
Okay. So, is the infrastructure there to make a custom one?
You should ask Daniel.
Okay.
We have a bunch of them that are.
But it's running as a single run, because you can always do that by running like multiple single points. It just becomes. That can be very efficient. It's just hugely painful to deal with.
I think it's basically a global data set with 90% of the world masked out as ocean. So that's all you're doing. Is
Oh,
you're taking
yeah.
you're just taking a surface data set
Okay,
and
that was something
making
I actually
everything
wanted to talk to one of the engineers about, because I actually have been making my own surface data. So I was wondering if I mask them as mask areas I don't want to simulate as ocean, whether they have zero overhead, just reduced overhead, or like how much I can gain from that. Because it wasn't clear to me whether there was any real. The big thing is whether the processors would deal with them differently. I didn't want to have, if I masked
Right.
like if I had a circle of stuff I wanted to do, only the grid cells in the circle, and then I wanted the middle and the outsides of that rectangle to be gone.
Yep.
I could end up with a situation where some of my processors had only ocean on them and they're not doing anything. So I didn't know how the couplers work, deal with that.
I can't tell you that.
Okay.
You can ask somebody.
All right. Well, it's got my juices flowing, as you can see, and that's all that matters. And my juices are flowing for lunch as well. So I'll leave you because I'm sure your juices are flowing for lunch. So thanks. Appreciate it.
Yeah. Go. Feel free, definitely reach out if you need help with specific applications, but it seems like the sparse grid has been a pretty productive way to do global runs without just focusing on a region.
Yeah, I was thinking about it. I've been thinking about it for my own purposes, but really it was some of Polly's questions and the things she was dealing with that was making me think about ways to do regional runs that would capture without going to low resolution where you lose topography and other different, like to be able to do if you wanted to do her Western US, you could do a couple Sierra, a couple, all the different stretches that you needed to get and run a run where you're only simulating like 10 grid cells versus 10,000 at high resolution and still be able to capture in a parameterization
the gradient
experiment. So it's exactly what you're doing, but for a regional. So yeah,
that makes sense.
Cool.
Yeah. Nate, can I ask you a question before we get started?
Yeah.
Maybe this will come into your talk, but I'm curious what SWE products you guys are thinking about for ILAM.
Oh yeah. No, I'm not going to talk about that right now. I need to loop back around with Lawrence. Medirk, I think his name was.
Yeah.
He had some that he was working on, but we kind of like lost momentum there, and so I don't have his latest thing and how he wants to release them.
Okay. Cool. Yeah, I was curious. There's a ton of data products out there, and I didn't know if anyone had. I don't do that work, so I didn't know how much people have put into the strengths or weaknesses of all of them.
I'm just kind of like a data liaison because I work with everybody, but I don't actually know.
Jack of all trades.
Yeah, master of none.
Yep. I wasn't going to say that, but I feel that way often.
I think we all do.
Yep. I feel like that's one of the values of ILAM is you get at least some sort of consensus about which data products are, strengths and weaknesses, I guess, of different data products. And hopefully if they're informed by expert opinion, the rest of us can be trusted.
Yeah, that's the hope. It at least exposes you to things that maybe you didn't know existed.
Yep.
I get a lot of comments from people who just go and grab our entire data repository, not that they're going to run ILAM, but just because they're curious like what's in there, which is both like impressive and a little scary.
Great. The new go-to shop. Yeah.
But I think it kind of speaks to what data centers should be trying to do to make data like collections like that very easy to mass download.
Right. Yeah. Well, and it's somewhat curated in the sense that it's
in format, like it's in some kind of relatable format across data sets, so you wouldn't have to build as much infrastructure to use it.
Yep.
Yeah, good point.
I just think about how much effort goes into just loading a new data set every time I want to look at one.
Yeah.
Tools are getting better, but it's still some work.
Yeah. Abby, I'm going to go ahead and mute myself because everyone's in my house today, so it's really loud. I'm used to be having the whole house to myself. Now it's like everybody's here.
I gather it's a snow day.
It's a snow day, yeah. They had to log on and do some schoolwork, but that all ended by lunch. So.
Should I wait another couple of minutes, a minute or two, or 1 minute maybe to get started, Will, or should we go ahead?
Sure. Yeah, you can go ahead and wait a minute. You can pull up your share your screen, Nate. I think, aren't you first in the session?
Yep.
Yeah.
It gives me some time to set up a timer.
All right. I think we'll go ahead and get started with the afternoon session for the Land Model Working Group, Biogeochemistry Model Working Group meetings. I'm Abby Swan, for those who don't know, and I'm the co-chair of the Biogeochemistry Working Group. We're going to have a series of lightning talks this afternoon, loosely grouped around new model features, and then we'll have some time for a discussion at the end of the session. So since we only have 5 minutes for each of these talks, we'll go ahead and jump right in. First up, we have Nathan Collier from Oak Ridge National Lab. Go ahead, Nathan.
All right, thank you guys. The context here is methods, general methods for benchmarking our land models, and want to present an idea we have for leveraging community consensus to assess some of our subjective decisions. One of the big criticisms or comments I get about ILAM all the time is that they read our paper and say, oh, but you make all these subjective choices, and why not it be objective? But of course, like, everything you make is a choice, and it affects the outcomes of benchmarking. So for example, when we go to benchmark the bias, we normalize that bias by the standard deviation of the variable, the reference variable, and then we map that normalized error to the unit interval. We like things on 0 to 1 using the exponential, and then we integrate over the globe, weighting by the mass of the variable. And this is intended to kind of filter out places like GPP over deserts, where the relative error is going to be large because of noise, but we don't want that in the score. And we claim that this is a community consensus. This isn't something we dreamt up in a day. It's something that we've talked about over a long period of time. But the problem that we have is that we really don't have a way to demonstrate that we actually captured the community consensus apart from the discussion and trying to find agreement among people. And furthermore, as you can imagine, we have many competing ideas internally. And how do you decide among ideas? It's very difficult. So this talk is to present an idea about how we might do that. So what I did first was I made a feedback form. If you took this form, it's available at ilam.org/crowdsource. Thank you. And please take it again. And if you're seeing it for the first time, take it now. And in that feedback form, you're going to be presented with a series of bias maps. Those bias maps are going to come from pairs of models out of the CMIP 5 and 6 eras, but I'm not going to tell you what models they are. I'm going to keep you honest. And then we're going to select from variables like GPP and sensible heat and surface area temperature, where I'm going to show you bias relative to the FluxCom and CRU products. And I'm going to ask you, which one do you think is better? And they're going to look like the plots that I have listed down here. And I'm not going to tell you what better means, because what I want to try to do here is capture what you think is better implicitly. And so I'm going to do that by using ALO's rating algorithm. If you don't know, Arpad Alo was a physics professor and a highly ranked chess player. And he actually created a ranking algorithm which models your skill at the game as a normal distribution, which evolves as matches are played and results are obtained. So this is widely used in football and all sorts of things to rank players, tennis, cyclists, fill in the blank. So let me give you a rough idea of how it works. Everybody starts off with a uniform rating. So in this case, like, I'm showing you 2 maps and both ratings are at 1200. If let's say that the right map is selected as I've shown here, then 5 points are transferred from the loser to the winner of the selected model. It's a zero-sum scheme. But if, say, the right map was rated higher at 1400, then if it was selected, that's the expected result. And so the number of points that are transferred depends on the difference between the expected result and the actual result. And so in this case, it's only transfers 2.4 because the player that was better, or the map that was higher rated, it was selected. But if the unexpected thing happens, like if the left-hand side was chosen in this case, then a lot of points get transferred. 7.6 in this case. And so that's kind of a rough idea of how it works. And I can use that to develop a rating from the results that I get from all you lovely community members. And so every dot here is one of those models in the 3 different variables. And what I'm doing is I'm plotting that rating against the bias score that we compute. And what you see here is really good correlation. I mean, I was surprised at how good correlation, which I think indicates that we produced a methodology that's at least sensible with respect to kind of what the community thinks about model performance. So a few details about this plot. The X error bars here are 100 random perturbations of question ingest order, because it's not like a sports season. Chronology is not the right, is not the only way to parse this information. And so I'm trying to show you that the ratings are quite stable. And we only evaluated maybe 66% of all pairs at least once, and sometimes as much as 6. So This is really just kind of a teaser. We have a preprint here that you can go check out where I give some full details and show you a detailed comparison of ratings, including the maps that I'm showing you down below here. And I guess what I'd like to leave you with is that I think this is an interesting idea for how you can get scientists' opinion without directly asking, but rather by looking at their choices. So hope you find something interesting there, and thank you.
Great, thanks. And maybe you could drop the link to that preprint in the chat. We've already got the link to the place where you can go submit your own choices if you want to participate in the data gathering. Next up, so we're going to move on again because we have lightning talks. So we'll come back for a discussion later. Next up, we have Sam Rabin talking about sowing dates and maturity criteria for crops in CLM. So you can go ahead and share your screen, Sam.
Sorry, 1 second. I got Zoom updated and now I have to give it permission to share my screen. Screen recording. This is a great thing to learn right now. Okay. All right, are you seeing that?
Yep, looks good.
Great.
And we hear you.
Okay, cool. Right, so hi, I'm Sam Rabin. I'm with Rutgers University, and I'm right now working on adding prescribed sowing dates and maturity criteria to crops in CLM5. So the way crop seasons work in CLM5 right now is that each crop has a designated window that can be a few weeks to a couple of months. And within that window, if certain weather conditions are satisfied, then the crop is planted. If the conditions are never satisfied, then it's not planted that year. These windows are constant per crop and they differ per hemisphere, as you might expect. And they're plotted there on the right. Harvest occurs once the crop has accumulated sufficient growing degree days. And this is basically a measure of how warm it has been for how long since planting. So we can refer to this harvest criterion as the GDD target, which is the amount of growing degree days required before you harvest. And again, that's constant per crop. And I should also point out that it's not just harvest that depends on this parameter. Other phenological processes are also a function of it because they relate to how far along in the growing season are you. However, for compatibility with model intercomparison projects, those use a standardized crop calendar. Most recently, this phase 3 crop calendar published by Jonas Jägermeier. He's working on a paper, but it's up on Zenodo now. I encourage you to check it out because it's really impressive work. Half degree resolution for 18 different crops, and it differs by rain-fed versus irrigated. So this data set provides prescribed sowing date and harvest date that are supposed to be used in the model intercomparison project runs. It's easy enough to bring in sowing date. I can just tell CLM, all right, if instead of planting sometime in this window, just plant on this one given day, whether the weather criteria are satisfied or not. But it's trickier to prescribe harvest date. And the reason is that you must ensure that the crop is always harvested at maturity, right? You need to harvest earlier if a year is warmer than usual, or later if it's cooler than usual. So instead of prescribing the harvest date directly, what we're going to do is prescribe the growing degree day target. And we're calculating that as the mean growing degree day accumulation for the MIT prescribed growing season over some baseline period. And it's a little convoluted how we have to do this. The idea is that we first run CLM with the prescribed sowing dates using a baseline climate reanalysis for the baseline period, that's 1980 to 2010. In CLM, we tell CLM don't harvest the crop until 364 days after planting. The reason for this is we don't want to have to read in the harvest dates, and this provides some flexibility. So CLM spits out the GDDs that have been accumulated since planting for every grid cell every year. And then I use a Python script that takes those and combines them with the prescribed harvest dates to find the mean growing degree days accumulated for each crop in each grid cell. And we're referring to these as the cultivars, right? So the way to think about this is a variety of crop that has been optimized to grow in this grid cell. And then from there, we can use that as an input along with the sowing dates into CLM runs with whatever climate forcing we're interested in. So something else that's kind of interesting, the infrastructure I'm providing or I'm building into CLM can be built upon, I hope, for adding other regionally varying cultivar parameters. So maybe some places have cultivars that are more drought tolerant than others, for example. This is something that's been talked about for various reasons for a while now. So I think hopefully this would provide a leg up for that. I warned Will that I wouldn't actually have any results to show, and I was right. So stay tuned, and I'm happy to answer any questions during the discussion. Thanks.
Great, thank you. Will, how are we doing on time?
We've time for a quick question while we transition if you want.
Anyone wants to type in the chat, or we have Joshua has his hand up. Go ahead.
Yeah, so I'm not super familiar with the crop model, but I know there's a grain fill function there. So why are you using growing degree days as opposed to like looking at grain fill or something else to basically determine when the crop is actually ready? Like basically a physiological versus a climatological approach to figure out when things are ready to harvest.
So the grain fill, when the grain fill begins is actually a function of this growing degree day target. It's basically once you're sufficiently along in the season, maybe like 80% of growing degree days accumulated, that's when grain fill begins. And I don't really know how it works in CLM, but from my previous models, as you get closer and closer to the harvest criteria being satisfied, allocation is shifting totally. So you can think of it as, you sort of are looking at some kind of physiological based method because they're one and the same, right? The physiology is determined by this climatological process.
Great. Okay. Yeah. Sanjeev, go ahead and bring your screen up. I'll just say on that last thought that I think senescence has a lot to do with why the season will end for a crop. And so it's very potentially heat accumulation related and not just how much is accumulated in the grain. All right. Sanjeev, go ahead.
Okay. Good afternoon, everyone. Today, I'm going to talk somewhat away from the research, something about education and particularly how the CLM Neon tool has made at least teaching CLM much easier than it was. So thanks to Danica and all the team for sharing this tool, and that helped us a lot, including the tutorial. So I'll just describe what was the experience in teaching in the classroom. You just need three things to run CLM. You need Docker, you need Jupyter, and you need your laptop. If you are attending this meeting, that means you already have everything. You can go ahead and run CLM on your laptop. Okay, so this was a graduate level course, and there were 5 students that those survived until last. So I put their name. They need the recognition for surviving my class. It's both theory and as well as the lab. So I covered like two classes in a week, theory and then going into the lab portion. The way I implemented this tutorial was, first was in class lab. And while first time it was implementing, it took us some time, for particularly first 1.5 hours. That Docker issue took us quite a bit time to get everybody to the speed. Still, we could not resolve some of the Docker issues. So we needed help from the IT department, and they were able to help and figure it out. So yeah, after the first lab class, everybody was able to run it with the help of the IT department. And then I assigned the assignment, everybody to a different site, so that to make sure that, yeah, they can run CLM on their laptop and do some analysis and visualization with the tutorial. And then more interesting was the final project where they were asked to do the parameter sensitivity experiment. So they can run at least 10 of those simulations, and they were divided into 2 groups. So I'll share result from at least one group. So this group did the local sensitivity experiment for the OSBS site, and they came up with an interesting method, and they call it local sensitivity experiment. They did it for 2 of the parameters, latent heat flux and GPP. And yeah, I would suggest not to read all the numbers, but interesting point was they could implement all these things within a span of 6 to 8 weeks. So early October, Danica shared the tutorial with me, and then I implemented in my class, and they were able to take it on from there. Scientifically, I think one thing was interesting to me. They found that for the latent heat flux, it is Madeline slope that is getting highest ranking. And for the GPP, it was the leaf CN that they found in their list of the parameter. But they can do it all using their laptop. Okay, so we'll finally hear experience from a student here. Let's see.
Hey folks, I'm Anna Costa, a PhD student at the Auburn University, and last semester I took Dr. Kumar's class called Land Process and Climate Interactions. So in this class, I had my first contact with climate models and also with the community land model, CLM. And I thought I didn't have previous knowledge in this type of model and also in Python language. I could learn how to use the model, mainly in new on-sites. And I think that was a consequence of very good documentation and of the tutorials that were available, and with a clear language and step-by-step can lead the research and they use easily the model. I was so excited for the model that I had also used it in other projects to analyze the behavior of wetlands in Florida. Was a good experience, and I intend to continue using this very complete model in my research.
Okay, so you heard about.
Hey folks, I'm Anna Costa.
Okay, so this is my take. You heard about the student and what they did. Yeah, my take on this tool is, yes, this has expanded the student's perspective on how to use climate model and how to even see what is the climate outcome or climate model output, so that they can go ahead and change the parameter setting and obtain a still, like in an experimental way, a different climate outcome. This may open new frontier in data modeling and understanding our changing environment. So thanks to NCAR Neon collaboration team for all their hard work. Thank you.
Thanks, Sanjeev.
Yeah, that's great. Really exciting to see that you're already using it to work in the classroom and get more folks involved in being able to access using CLM. So I think we will move on to the next talk. Yeah, we can come back and have more discussion about that later. Next up, we have Naoki Mizukami. Naoki here.
Yes.
Excellent. So, recent progress in river modeling. Go ahead, Naoki.
Yes. So I'm Naoki Mizukami. I'm a hydrologist doing a lot of hydrologic modeling at the NCAR Research Application Lab. So I'm going to talk about recent progress on Mizu route improvement and also some of work done coupling. So actually we have 2 already two routing model, RTM and then Mozart, and then trying to add one more middle route and then wonder why. So biggest maybe benefit in the middle route is spatial discretization. So RTM Mozart use coarse gridded river network, but middle route is more flexible. You can use grid, but also use catchment-based spatial discretization. This is kind of, we can think about unstructured grid. And also application, RTM Mozart has own kind of application target, but middle route, try to make middle route more applicable to many applications. So we can run middle route CTSM together. So basically one-way coupling. So we can do taking CTSM to the runoff, go through mediator coupler, and then remap to catchment, and then route through river. So this is kind of summary of work completed. Yes, we finished one-way coupling, and then we have we set up two catchment-based river network data set. One is coarse HDMA, and then second is melt tidal, which is much higher resolutions. And then also we have CTSM grids combination with many random model grids, and then two catchment-based network data. In terms of middle route development, so far we've done 4 things: parallel computing, and then I recently added more routing schemes. And then biggest thing done so far, Ina was talking this morning for lake. Yes, so this is the biggest thing we've done. And then I'm gonna just the rest of my time spending 2 things for this, maybe 3 more slides. So I added recently two more routings. So I'm sorry. So we had a 2 routing scheme already, and then one is IRF, and then the second one is KWT. So IRF is super fast, can be used for long run for climate change study. Can run in 1 second, couple of seconds for 3 million reach, but kinematic wave is more like a complex. You use the Lagrangian approach, so it takes 10 seconds to do 3 million. So more like flat forecast application. So I added more intermediate routing scheme, which is more commonly used for like more community for hydrology. So Muskingum-Kanj and then diffuse wave. Both account for wave attenuation, and especially diffusive wave, we can take into account backward effect. So this is nice and much faster than the KWT. And I started testing and then looking at the 4 different routing schemes. And then this is like showing simulation of stream flow at the mouth of Columbia River. And sorry. Sorry. Oh no. Oh no. Sorry. So top is hourly, and then second is daily aggregated, and then third is monthly. So hourly, you can see a lot of scatter comparing diffusive wave versus 3 different routing schemes. But if you aggregate monthly, especially less difference. This is an uncalibrated IRF routing scheme, so you can see small difference. But if you adjust parameter, you can pretty much match up with monthly flow for all routing schemes. So like a flat forecast application, routing scheme is more important, but the monthly scale, like climate change study, maybe routing scheme is maybe not important. So lake, so I'm just showing what the Siobhan did, Siobhan from University of Saskatchewan. So he connect hydro lake, 4,000 lakes into like a HDMA river network. And then this is showing distribution of lake. And I think showing only like a river reach connected to lake, and then color code indicating how lake routing, lake model impacting stream flow, the downstream. And darker color is more impact. And if you go downstream, especially looking at the zoomed in map, if you go downstream of lake, it's more less impact from lake.
Thank you. We should finish up.
Yes, that's all. So
Perfect.
thank you for 3 people from big contribution.
Excellent, thanks. So we'll move on to our last lightning talk, and then we'll have time for a discussion. So if you have questions for any of the speakers so far, you can go ahead and put those in the chat, or get ready to raise your hand when we're done. So next up, we'll hear from Sean Svensson on an update on hill slope hydrology. If you're there, Sean.
Yeah, sorry, can you hear me?
We can.
Okay, so of course I'm at the end of my, let me get to the beginning. Oh, come on. Okay, yeah, so I'm just going to talk briefly about some just some recent work with the hill slope hydrology model. Quick synopsis of this. If you're not familiar with it, it's basically a multi-column version of CTSM based on this concept of representative hill slopes. And now we have inter-column communication. And so we're explicitly modeling the redistribution of soil moisture. It's also enabled some bidirectional stream soil column interactions, as well as some meteorological downscaling. Okay, so the summary, since this is a short talk, is with this new NUOPC cap and the ESMF regridding, CTSM can now be run on these irregular grids, and specifically something like a catchment. Another new feature is that in the single point mode, which some people have been using, we can now model stream flow within CTSM as opposed to needing a routing model. And then finally, we've generated taken a first stab at generating global hill slope parameters and run with that. Okay, so this is an example of unstructured grid or irregular grid based on catchments. So you can see all the sort of different forms of the catchments. This is just derived directly from a DEM. You can also see how things like lakes can be combined into their own polygons, and you can run the model this way. So here's some example of output. So you can kind of see where these individual catchments are. This is gridded at 1/8 of a degree, but the actual catchment resolution is comparable to 1/2 degree. But so now you can kind of see what the difference is of what this might look like in terms of a simulation. What tends to happen though is catchments tend to be aligned with the gradient of topography. And so they tend to be aligned sort of across across the topography here, but you can see how the way this occurs with averaging of the meteorological forcing tends to sort of bleed the forcing across this gradient. So for example, here's this high topography zone in the Sierras, and the catchments trend along here, and leads to some undesirable features. Again, also correlated with this are things like vegetation, where you tend to have forested mountainous regions and either crops or grasslands in the valley. And so another feature I've added, in addition to doing sort of this catchment modeling, is to be able to split up these catchments. So we can subdivide the catchments and look at just sort of high elevation catchments and just low elevation catchments, and do kind of a subdivision and recombination. And so when we do that using catchments that are also connected to the topographic gradients, then you can see we have, in this case, temperature variations that align more closely with the topography. And the implications of this are, we can generate these polygons based on something like a hydrological catchment, but also things like land cover type or the atmospheric forcing, and so that we might be able to get better correspondence between these and eliminate some of the issues related to how averaging is done across these. The next thing I want to talk about is, so we have these stream channel interactions where for a given hill slope representation, waters move from high to low, but we also have an interaction in the lowland column to the routing model. However, if you're running in a single point, you don't really have a routing model to run with. And so that's been a complication. So I essentially took a part of the routing code that was in Mozart and added it within CTSM. So you can run CTSM separately in a single point mode. And so now if you have a single point with multiple columns, they now have this lower boundary condition here that will evolve dynamically. And then the second benefit of that might be that there's another observable. So if you're modeling a catchment, now you can look at what the stream flow is and maybe compare that to an observable. And then this just shows an example of what that output would be in terms of discharge, stream depth, and just the total volume that comes out of that. And then finally, this is just an example showing that we have actually derived global hill slope parameters. This shows different columns. So this would be the lowland column. This would be the upland column, showing the differences in height for those. And so basically you take all this high resolution 90-meter topographic data and you do a bunch of processing to determine the stream networks and the catchments and therefore the hill slopes, and you end up with these 6 parameters. So for example, the distance from the channel, the width of the hill slope, the overall slope within the column, the area, et cetera. So that's just a flavor of what we've been doing now, and the idea would just be maybe you could think of ways that this might be of use in your own research. Ongoing work would be what I showed you is for sort of a specific spatial scale for that global data, but we think that the spatial scale is going to vary regionally, depending on what the overall kind of variance in the topography is. And so now we're looking at, well, what would be the most representative for each region, whether it's a flatter region or a more mountainous region. Is there any kind of fundamental effects just by using this irregular mesh versus a gridded lat lawn? You can see how the averaging that's done in the coupling is going to impact what the model sees. And so is that going to be a large effect on sort of our simulation results, or is that going to be not meaningful? As I mentioned, we have the meteorological downscaling and the lateral flow. And so, we've seen talks earlier today looking at some of the biases and runoff. And so we want to look and see if the hill slope model, including these effects, could have any improvement or benefit for those kind of issues. And then finally, looking at lateral flow in these seasonally and perennial frozen soils and permafrost regions and things like that. So that's it. Thank you.
Great. Thanks, John. So now we have about half an hour for discussion, open discussion on this last set of talks of new model features. I see we had one. Go ahead and raise your hand if you'd like to ask a question verbally. And it looks like we had some questions in the chat. One from Sanjeev asking Naoki a question. Sanjeev, do you want to ask that out loud? It looked like maybe Naoki already answered as well.
Yeah, so I was looking for a mapping file from the river network that is in CL numbers is what we get it from the USCS, and it looks like, yeah, mapping those two are a little difficult.
Excellent. Polly, go ahead.
This is a question about hill slope, Sean. If you're running with a catchment instead of a gridded, does that mean that all of the forcing data, the atmosphere and the land surface, is that all then put in a different form, or is it still ingested in the gridded form?
Yeah, that would still be, everything there is done within the coupler. So you'd still give it the standard kind of formulation. The question there is just now you have a different underlying grid. And so how that gets averaged. So for example, before, if you have a grid that spans both, the Central Valley and part of the Sierras, you're going to get this averaged meteorology. But now if you separate those out, then you'll get something more representative of each of those. And then you can kind of see what the impact is on the model in that way.
So does that come in as like another domain file, or is that how is the resolution and of that, the mesh that things are averaged over, how's that determined?
Yeah, that's right. So with this new NUOPSI, whereas before we had these domain files, now we have these, they call it ESMF mesh files.
Yeah, I have it.
And so, yeah, so now you would have this ESMF mesh file, and there's overlap with the standard kind of gridded things, but the new thing is that you can have this unstructured, irregular, kind of polygon based grid that you can now just stick in there and it'll work the same way.
Awesome, thanks.
We'll go to Joshua next, and then Charlie, and then Will. So Joshua's question is, how is groundwater connected between hill slope units? Can they be connected in different ways than the surface stream routing?
Yeah, in this context, it's not really related to the stream routing. That you have a stream network, and then if you want to consider a reach, every reach would have sort of orthogonal that is what your hill slope is, and so that configuration is separate from that, and those are connected based on the water table within each of those.
Excellent. All right, Charlie, you're up next.
Yeah, I have sort of the converse question to Polly's. How do you visualize the output when, Sean, when you're doing the catchment based?
Yeah, so now that's one of the maybe the downsides of using these kind of approaches. It's no longer simple to do like a quick raster plot, and so there's an additional step there where you need to regrid. So in that case, that first thing I showed you, I regridded those catchments to an 1/8 of a degree, just for essentially the visualization of that. And so I have scripts where you can imagine just having that run inline, and modifying your output as it's created and just generating gridded files directly from the vector files. And then you would just work with your gridded files. But yeah, you have to put it back on some sort of Latlon or whatever grid in order to visualize it.
Thanks.
All right, Will, go ahead.
This is more just, I guess, building what Sean was saying. So we kind of, we saw in the first couple of days, like with Jackie and Polly's work, these regional applications of FATES with CTSM are really important. And then Megan and Adriana are building tools to help run those regional cases within CTSM more easily. Sean's done a lot. So, and Sean's right, like, the new OPSI cap got rid of the need for a domain file, but now for a regional case, you need a mesh file. So Sean has a script that generates the mesh file that you need. And then we're working on putting that into a workflow that makes it easier for people to set up their own regional cases. I'm sure I oversimplified that, and I don't know what the timeline, hopefully this spring-ish, that'll all be kind of up and ready to go. But that's one of the things we're working on for documenting. And Sean, a question I had for you then. So with these hydrological response units, do you still have, I'm assuming you still have upland and lowland columns within each of those HRUs? And so then same thing, like, is the mapping, I've only done hill slope on single point. So you just have to kind of keep track of your columns within each response unit to make sure that you're looking at things correctly, I guess.
Yeah, it should be kind of the same thing where you have metadata based, telling you all that kind of information. But one other comment I was going to make, I don't know if I stated it very clearly, but that the idea of using catchment meshes and things isn't particular to hill slopes. You could use it for whether it's a single point or a standard, CTSM simulation, if there's any benefit to doing that to more accurately kind of capture a region or a site that you're looking at. You can use that same thing irrespective of hill slope being on or off.
I think this question in the chat might be related, so I'll bring it up now. Matt V asked if the column structure per representative unit hill slope is the same as the standard CTSM, and shouldn't it be a pre-processing step to get the hill slope delineations based on a few parameters?
I'm not sure I totally understand. It's not the standard CTSM, there's just a single column, and this is now running with multiple columns within every grid cell, so it's fundamentally different in that regard. And then with the additional feature that those are now connected and actually passing information, for example, the fluxes of subsurface lateral flow back and forth. But it is all pre-processed. You have to, whether it's, our first paper we did was just like analytical expressions for what hill slope shapes might be. And then what I just showed now is that we can also do this, in kind of a big data way globally. And it is a fair amount of data to generate that using these 90-meter global DEMs is something like a terabyte of data that, they have to distill down into an individual surface data file.
Yeah, I was just wondering if within the column, the averaging for the surface, like the PFTs and crop stuff, how does it happen within HRU columns? Like which PFTs go where, and in that term.
Yeah, I mean, we don't have, so that would be a place where we're kind of thinking about in the future. But right now, either what would happen is you would get reproduced all the same distributions of, for example, PFTs on every column. But then I also have subroutines within the code where you can specify, for example, if you wanted forest in the upland and grass in the lowland, et cetera, you can do those kind of redistributions after the fact as well.
Someday, maybe you can let fates figure out what to grow where. All right, Dave is up next.
Yeah, my question was for Sam. Curious whether with this sort of inverse GDD method, if you've plotted up like what the GDD looks like everywhere, and does it look like sensible? That's one thing. And then the second is like, I think we talked a little bit before about for specified planting date, making it more like a specified planting window, but it's a spatially variable. That makes sense, rather than crop variable. And have you thought at all about that? About how to implement that? Or
all right, so the first question, I have plotted the GDD cultivars that I generate, and they don't look sensible because I had some problems reading in the sowing date file. So that's what I'm bug fixing right now. The other question, have I looked into regionally varying sowing windows? No, I have not looked into that at all. Theoretically, the code I'm building in could be expanded to build that kind of functionality on top of it. But at this point, I haven't thought exactly about the hard part would be going from these prescribed sowing dates to a window, right? And the sort of assumptions and logic that you use for that process. And I haven't given any thought to that.
I want to jump in and use my moderator's privilege to ask a sort of related question, which is you're basically back calculating what you think the length of the growing season is in like a location specific way based on existing data. I don't know a lot about the MIP that you are referencing, but how do you think about like running a crop model structured in that way into the future? So we think there should be regionally varying cultivars, but you don't expect the do you expect those cultivars to stay the same over time? Like how would you account for that? Is my question.
It's an extremely good question. Right now, the cultivar files that I'm generating are just single values, right? So it's constant throughout time. But the capacity is there for them to vary over time. Question is, are we going to have the data to parameterize those? And yes, actually, because some of the the MIP runs I was talking about are part of the sort of initial phase of the intersectoral impacts MIP. And in this initial phase, we don't consider adaptation at all. And in the crop sector, pretty much what we think of when we think of adaptation, at least as far as what our crop models can represent, is sowing date, harvest date change, as well as cultivar shift. So someone has been working on, Sarah Manoli has been working on a time varying sowing and harvest date data set based on various sort of weather and climate parameters for each crop, and of course, geographically varying. And so then from that, I would be able to generate the growing degree days that are updated throughout time. Throughout time as climate changes. And so a simple way you might think of that is instead of the growing season just getting shorter and shorter as things get warmer, the growing season might stay a similar length, but the cultivars have a higher growing degree day threshold, right? So they're actually able to accumulate more biomass during that time.
Yeah, maybe changes in leaf area and structure as we saw on Monday.
Exactly.
Okay, how about Katie's question next?
Yeah, I have a question for Nate. That was really interesting to see the ILAM survey results. And I was just skimming through the preprint, and it looks like there's certain metrics and variables where the humans and the ILAM scores agree more than others in terms of like the correlations of those scatter plots you were showing. So I was just wondering if you had thoughts on what we can learn from that, if those results make sense in terms of where there's more agreement or less agreement.
Yeah, I mean, it's a hard question. We were trying to look regionally, so we kind of were wondering if we could hone in and say, okay, well, mostly people are just looking at the tropics or something. And what I found was that wasn't true. Like if I just plot and look at correlations with respect to scores over different regions, I found not as strong a correlation. So we were kind of looking at that. I haven't really thought much about temperature versus GPP. GPP, there's a little more width to that line, that correlation line. So I'm not exactly sure why that may be. It's maybe not a satisfying answer.
No, it's okay. Thanks. It's really interesting.
Go ahead, Dave.
Sort of a follow-up for Nate. So your work on this preprint, but if people went ahead and did more, whatever crowdsourcing, would that be able to fold into the paper before it goes off? Like we put the link in here. I don't know if you're actually collecting data, if somebody went and did it. Remember earlier you said that you wished post-fact that you designed it slightly differently, that there were a lot of like pairs that were like too obviously different that weren't that useful.
Right. So a couple of things. If you want to go and take that and have everybody in your lab take that quiz a bunch of times, we would love it. For starters, I would kind of reset the record, and so I would have a way to kind of validate. Under two separate occasions, we got kind of the similar result. But I would also just lump all the data together, and I can regenerate the figures pretty quickly. And I lost the other part of your question, Dave.
Well, it was about redesigning the way you did the poll, because there were a lot of, whatever competitions that were actually not that meaningful because they were a clear winner.
Yeah, so I did all of the ratings offline. I just collected the data and then I generate the ratings afterwards. If I had to do it over, or if you are thinking of conducting such an experiment, I would recommend that you generate your pairs not randomly, but rather based on where their ratings are similar. There's a formula for getting the expected value of any confrontation, the result of any confrontation of two pairs, and you want to generate those such that that expected value is close to 50%. And what that does is it makes you get more information density where it's ambiguous, the difference between the models. That would be awesome, but maybe beyond the scope of what I'm going to do right just now.
Kind of follow up to and say, in the end, we were hoping that maybe we would learn something. One possible outcome could have been that the human eye sees something totally different than ILAM, and then that gives you something to target an ILAM, right? But that's not the result that we've had so far. And yet we're still, I would argue, we're still seeing results in ILAM that don't make intuitive sense sometimes. Do you have what would be your top thing to try to approach? And an example I'll give is that, the mean bias, I can't remember which variable it was for GPP, maybe for the global mean values could be quite different, and you can get a score that's pretty similar. I was noticing that recently. I can't remember what set of models or whatever we were looking at, but so like, why is that happening was a question I have. But do you have anything that you think would be the best next thing to work on to try to improve the robustness of that?
So this is something I periodically try to fix. And so last December, I lost a week of my life trying to figure out how we could fix this kind of a problem, because a lot of our scores end up very close together. And as far as I can understand, it's due to kind of the globally integrated nature of things. And I think more and more what I'm settling on is that, the bias maps that we show you across all models and all variables and all data sets, it's a lot of information to parse. And so it makes sense to try to synthesize that information somehow and give people less information that they can try to get an understanding of what might be interesting performance differences that they need to look into. But it just may not be, it may be too reductive to give you one single scalar for the globe. And we just have to move to more regions. But this is what I'm currently kind of looking at, but we haven't yet made it more useful. It's an ongoing process.
I have a related question to that, which I'm sure you all have thought about, but have you thought about having sort of regional versions of ILAM, not necessarily for deciding on whole, just to give that additional information, like maybe the Whitaker biomes, or maybe picking out some specific areas in particular and redoing the scores based just on those regions, so that you could, especially if you were checking certain processes, like hone in on what might be going on in particular places.
Yeah, and the Whitaker biomes in particular is a good suggestion. That we do have those. ILAM can be run over arbitrary regions, which you can make by kind of a paint by the numbers NetCDF mask, and that's currently up there even. Two things, and just recently we added Whitaker biomes, so you can go and look at results grouped by Whitaker biome. I think that's currently up. If it's not, then it should be soon. But the problem is that, and this is the problem that we find with users, is that if we present you with the global score, which might make sense, then that for some people is the only thing they look at. Or maybe you didn't even realize, right, that the regions are there. And so it kind of makes us rethink maybe how we synthesize that performance, so people are more aware that there are regional information that they can use. It's tricky.
Yeah, for sure. It kind of makes me think of Daniel and Katie's work of trying to highlight anything that pops out as really doing poorly in some region and highlighting that somehow. But it sounds like it's an issue of having so much information and presenting an amount that people can digest. So more information maybe doesn't help.
But we love suggestions. Thank you, everyone.
Joshua, go ahead.
Yeah, so this is another question for Dr. Collier. Do you have any, are all of the results that you're actually putting up for people actual data from actual runs, or are there controls in there that test for things like putting up a dominant solution over a non-dominant, just to basically detect whether people are actually consistently picking things which are better, demonstrably better, or ability to, like, looking at effects of the color scheme, for example, the ability to any qualitative things to say how much better is this one than this one, to be able to see whether people can detect what you actually are presenting as differences through the visualization.
Yeah, I mean, you could, once you realize that what it could do, you start to think about all sorts of questions that you could ask. In my case, I'm just giving you two plots and asking you which one is better. And so all I'm storing are the two plots I gave you and the variable and model that correspond to those plots, and which one you chose. And that's
so they're all real plots. None of them are ones you made up to sort of test like people's preference, artificially.
That's correct. And okay. I chose the color scale, tried to make something colorblind friendly. And I think I use like the middle 98% of the data for the limits of all the data for the limits. But of course, like if you change any of that, you could change people's perceptions. So it's kind of another interesting question, just not the one I was trying to answer.
Very cool.
Dave, go ahead. Oh, go ahead, Nathan.
If you have problems accessing ilam.org, it's okay. We're not like doing something nefarious, but the authority that issues certificates, I think Chrome on Mac no longer carries. So just try opening it in Firefox. And sorry.
Dave, go ahead.
It's not really a question necessarily, but a comment for Sanjeev and the rest of us is so Sanjeev has demonstrated that he can use this in the classroom successfully, right out of the, basically out of the box with a few little tweaks maybe. Do we need to think about ways to advertise this to faculty around the country, and how would we do that? Are we, maybe it's a little early to do that, but how would we do it? Anyone have any thoughts about that? Feels like a lot of potential there.
Adriana in the chat said a Visio series.
I have thoughts. That was very cool to see. But when I think about my own application, that barrier that Sanjeev came up with, which was the hardest one, which was getting Docker installed on and working properly on everyone's machines, would be the biggest barrier for me. So what are some approaches to, I don't know, this is not my space, but something that's more like a Jupyter hub, even if I could get it running myself centrally once, and then my students can access it through something like a Jupyter hub or something that is hosted by NCAR that students could run the code, would be even more tractable for reducing that first barrier.
Yeah, that's really good feedback, Abby. I guess I don't know enough about this, but they're increasingly offering more cloud-based tutorials with CESM, and CTSM is kind of trying to push a little bit harder on that. So I think having these in the cloud would maybe download that Docker barrier, and you just have to, have computing time or whatever on AWS or equivalents. Megan had other ideas.
So one possible idea might be to avoid running, going through that Docker, might be using binders, which is basically underneath they're using Docker, but the user will interact with them through basically online. So it wouldn't be they do not have to have that Docker installed on their own local machine. It would be online, and they will just click on it, and then it would open a Jupyter Lab notebook, a Jupyter Lab environment with the Jupyter notebooks, and the user can run it through there. That needs some cloud setup, but that's one solution. Basically underneath it is what Will said, is just a cloud and the Docker running on cloud. That's one possible solution that. Or
I can run it on my local machine cluster or whatever, but it's more just the barrier of getting every student to install something is a lot harder than me being able to control one install that works for everyone. Yep. Sanjeev, you have your hand up. Go ahead and comment or question.
Yeah, I had just a comment, I will be a new user to iLAM, so I have not used the iLAM, but I'm planning to use it. One of the things that I see why anyone would be interested, or particularly these kind of regional people or any faculty, if we find any correlation between the global performance of the model versus the problem that I am interested in. If I'm a water availability problem in the Southeast, is there any relationship between how the model performed globally and does that versus water availability in the Southeast? And if there is the relationship, then can I get some advantage of selecting the model or understanding if ENSO is more important for my region? Is it can it provide the regionally customized information in a way that can be applicable to many of the people?
Yes. For example, the NASA Above project has their own region, and they run everything through a region that they define. And so they just get all the stats just on that region. So you can look at regions. We have found that a fewer regions, at least for the goal of understanding kind of global decadal scale biogeochemistry, the fewer regions is probably better. But if you had a targeted region you wanted to run it on, then you can totally set that up and run it and take a look at what that tells you about your model. There are tutorials too, I'd be happy to point you to.
I guess I was more thinking about what is the relationship between the model global performance versus model regional performance. How does understanding the global performance helps me to choose the model for the regional scale? So that's why anyone will be more interested in seeing both the global performance as well as, their regional one. Some of my comments may be uninformed because I have not used islands, so sorry about that.
No, I don't know. I think it's an interesting question, but I don't have any particular insight for you. But I think that's an interesting way to think.
Well, we've come to the end of the hour. If I understand the schedule correctly, Will, this is the end of our discussion time and the end of the meeting for today. There's some great back and forth going on in the chat as well, and some different ways you might use the Neon containerized version of CLM. Thanks everybody for a great session. And any other announcements, Will?
I don't think so. Tomorrow at 9 for our last morning, and we're going to finish with PPE. So try to keep people in their seats.
Excellent. Excited to see everyone back tomorrow. Thanks again for all our speakers.
Thanks, everybody.
Thank you.